Hopefully that will work. Right, good afternoon. I hope you're refreshed after lunch and it was adequate. It's nice to see you all and welcome to everyone online as well. I hope you had the appropriate food item at the right time for you. So my name is, as Milan said, is John Elliott. I'm one of the senior academic fellows here in the Earth Observation Group. And I've spent quite a lot of years working on InSAR observations of earthquakes. That's what I did a lot of my early research on. So I'm going to show you some of those old classics that we've got, and more importantly, what we can learn about the world from interpreting the deformation patterns that you get from these kind of geodetic observations. Let's see if this works. Brilliant. So what we want to show you is to build on what you've been learning this morning, is what you get from Earth observation, and in particular InSAR radar observations of the earthquake co-seismic part. Later on this afternoon, I'll go into the Interseismic and I'll explain how that fits into the earthquake cycle now. Now, I appreciate you are from a diverse range of backgrounds. This is heavily leaning towards the earthquake cycle, but I'll show you how we use these observations to interpret the stars of faulting, the structures in the earth that generate these earthquakes, the shaking on earth, and how we build up the stresses and strains that are then ultimately released in these earthquakes. And then towards the end, we'll point you towards the practical exams going to do the dislocation modeling. So classic, using data through a model, trying to get an interpretation of the earth. And we want to do this, we want to understand active tectonics, active mountain building, crustal deformation. So how do we deform the Earth's continents? So you can grow geological structures like anticlines, look at how fast these faults are slipping through time before they release their energy on earthquakes. Where in the crust is it? Is it along the edges? Is it pervasive throughout these parts of the continents? What does it look like at depth? We're taking surface observations, but we try and infer something about the behavior of the Earth at depth. How do these faults segment as they go along the strike? Are they multimodal, single long faults? How do we interpret the structures? And how do we build up these pressures in the earthquake cycle? And can we understand something about weak and strong? Rheology, the rock rheology. What does the Earth's crust mantle do in terms of allowing these stresses to prevail? So onto the earthquake cycle. Here's an example of the North Anatolian fault that runs along northern Turkey. Imagine we're imaging with InSAR. We want to understand what goes on beneath the surface along the fault trace that runs through here. You can sort of make it out in geomorphology. Faults tend to affect the landscape. You can sort of trace these major ones in that landscape. And we want to look at two measurements. How is the fault slipping through time? And how is the Earth straining through time? So these are some things we want to know about the Earth. And strain builds up as the plates or microblocks move relative to each other. You've got differential movement, you're building up strain. Because this part of the fault is locked, it's not doing anything. The fault at the surface is building up strain, it's locked because the bits that is moving is deep within the Earth, say below 15 kilometers. So we'll go on to what these sort of dislocations may be, but they're shear zones. So they're accommodating relative motion. They're an idealized model. The real world does not look green in a straight line 15 kilometers down, but it's our way of interpreting what we see at the surface. Now, what happens in the actual earthquake itself is that strain has built up stress on the crust here. It's reached the point of overcoming the friction on these fault interfaces, and it suddenly goes snap. And it does that in a matter of seconds. You get rock propagation as it nucleates and runs along the length of the fault for many tens or hundreds of kilometers, generating these huge earthquakes that lead to ground shaking. Now, that gives you fault slip at the surface that geologists can measure. They can see how much these landforms are offset. And it gives you a sort of drop in strain in that area. It's a recovery of the stress that's been built up. Now, in the time after that, we've got various other bits of the earthquake cycle processes going on, termed the post-cycling, after the seismic event, in which we think different things are happening. But one of those is deep after slip on the downward extension of the fault into the earth. That sort of makes up the difference between what was creeping in the long term in the interseismic and what was slipping fast in the co-seismic. There's other processes that are going on in these after-slip zones, different but similar to where the aftershock patches would be around a fault rupture area as well. This relieves some of the strain into it, builds back up into what we get as the interseismic period. So we've got interseismic build-up of strain, co-seismic release, some post-seismic relaxation or after-slip, and then back into this cycle. So this is our simplified view of the way the world works. If everything worked that simply, it would be a lot easier as long as you knew how long it took to build up the strain, the failure stresses, in terms of forecasting earthquakes. It's not quite as simple as that, but that's our idealized starting model. Now, in the short term, we can use this to identify where the hazard is. So things that are building up strain might ultimately fail in earthquakes. You want to know where things are straining. And to assess the time dependence of the earthquakes, like what can we get from the post-seismic information that tells us about the way down-dip fault is behaving, the way the world works. In the longer term, we want to understand repeated earthquake cycles instead of over hundreds of years, maybe over hundreds of thousands of years. How do they build up between the distribution of strain, the tectonic plates, and the growth of these mountains? How does that all relate to quite challenging that these rates have actually persisted through time. Obviously, climatic effects are now actually unfortunately increasing these other impacts on the fatality rate, and depending on how you actually count and database these, it does vary a bit. But it's still been really quite a persistent and expensive natural hazard. Right, can I carry on from there then? But you're just not seeing the screen.
Oh, yeah. Sorry.
Is that now better?
Yeah.
Yeah, but thank you, Milan. So if we then look at earthquake hazards, this is the exposure to start with, then, which we ultimately would need to look at the risk. This is where people live, like Ganges, northern India. Mega cities where you've got over 2.5 million people concentrated densely in urban areas, probably in concrete, poorly reinforced structures. And we're often surprised by where these earthquakes on the continents intersect these human populations. And as I said, it's the long recurrence that makes it hard to understand any individual faults that may be in the system. And we have to look at understanding the global problem to apply our knowledge more locally. And we can do this through interpreting the geomorphology, as I showed you. The faults actually change the landscape quite a bit. They offset alluvial fans, they grow mountains. But another way of trying to do it is to look at the historical seismic catalogue. Where there's been an earthquake before, you might reasonably say there might be earthquakes again. That's the classic approach of trying to do it. These are some of the earthquakes coloured by magnitude, scaled by size in terms of fatalities. China has suffered some of the largest continental earthquake faulting events. But what we want to try and move to is an approach where you change not just where the earthquakes happened in the past, but where you're building up the pressure. So the latest sort of hazard models include where this pressure is building up. So the red zones are straining at a very fast rate, the strain rate. So they're building up that pressure. So it's got to be relieved somehow. If it's relieved seismically in earthquakes, you're going to get shaking. So that's that intersection of the Himalayan arc with where the people live, means you've got high hazard, but a high vulnerable exposed population creates a high risk. Now, we want to, an example of that, as I said, in China, it's experienced by a few of this, is Yushu, the concrete distribution of buildings here before an earthquake that occurred 2010. And then after, you can see the near total destruction when these faults run right through these cities. And thousands of people were killed in this event. And as a fraction of the population, it was many tens of % of the people who lived there. So if we then look at where there has been a past earthquake here in northeast China, where the geomorphology is a bit harder to interpret. Here's Beijing, with its many tens of millions of people in. This is Tangshan, one of the most deadly earthquakes. Its fatality rate is hard to get from historical records, but 1976, magnitude 7.5, so not the biggest kind of earthquakes that the Earth can accommodate. Unfortunately, ruptured again right through Tangshan. This area is really quite flat. The mountains are up here where you can interpret the geomorphology more. But being able to get a measure of how this area is straining would be useful for understanding where it's building up pressure. And just to hit home how quickly these populations are growing, here's Beijing Landsat imagery over time. The urban area is rapidly expanding. And just 10 years ago, there was 21 million, so there'll be many more people living in that area. And you can be very sure that the fabric of the mountain, the strike of this fault, means there'll be lots of faults that run under here. So increasing efforts are made to image this, to look for diagnostic terms, strain, differential compaction, subsidence that might all hint towards where the faults lie beneath the city. Because when they intersect the actual urban infrastructure, you get a large problem. So why has it been so difficult to mitigate against earthquakes in terms of understanding them as a physical process? Well, if we just take an example, synthetic idea of the recurrence interval, here earthquakes are happening in a very regular pattern. So they've got spacing that's every, say, 100 years. But in these other examples, they're not regular. So if the world works in a very regular fashion, then we could start to, predict them. If the earthquake was 90 years ago, we know we've got 10 years left. So if things with that approach, we'd have something to do. If it was normally distributed, we did, sometimes there's a big gap between earthquakes, sometimes a small gap, but on average they're about 100, so a small coefficient of variation. Then again, you could start to build up some idea. And some faults do seem to tightly cluster around this approach. So the Alpine fault in New Zealand has quite a well-known recurrence interval from the last 24 events. So it's a bit easy to do. But there are other ways that faults behave. Quantum failure, like a failure of a light bulb or a hard disk, depends the time independence between the last failure and the next failure, you just don't know. It may be on average every 100 years or so, but it just varies a huge amount. So if it was like that, that'd be very hard to do anything about. And then there's another idea along the Dead Sea Fault, for instance, that seismic events might be quite clustered, that when you have a big event, you're actually much more likely to have another big event than long periods of hiatus of no events in between. So we don't know, we don't have enough measurements to even get an average, and we don't know how the Earth behaves in terms of its recurrence interval. So there's a lot of unknowns here in being able to understand whether it's periodic, random, cluster, quad. We just don't know whether they're that, and we wouldn't even be able to measure them because we don't have enough paleoseismic information in most places to dig down and build up that. So that's really one of the big reasons why it's been hard to really predict these earthquakes. The time to failure is not really known. So what we try and do is contribute our bit to Earth observations to the disaster risk management cycle, is using our various sort of satellite platforms to feed into different parts of the research and applications that occur within this earthquake cycle. So the co-seismic bit, one, the earthquake's happening, you can try and understand what has happened. You can't do anything about it, but you learn from each example a little bit more. The response after the earthquakes, a lot of people use satellites for damage mapping, landsliding, things like that. In the recovery period, you might try and understand how the stress distributions, the interactions might promote failure when other faults around. We've worked on sort of mapping cities to try and map out where the buildings are, how high they are. That are useful for some models, so that's using optical DMs. And then in longer term preparedness, it's trying to map these strain rates, at least knowing where the pressure is building up might provide some help in trying to focus resources around the areas that strain the greatest. So getting to this continental strain rate field from InSAR is a lot of our most recent work. And you're focusing largely on the SAR satellites here, Sentinel-1, but there's been really quite an explosion from the early sort of observations from the ESA platforms, say ERS and MVSAT, through to the workhorse that Sentinel-1A that's producing large volumes of data, and the anticipated ISAR missions that are coming very soon this coming year. So there's been a huge explosion in the availability of data that's changed the way we've been able to do this much more systematically rather than individual case studies, and to move from earthquakes to the longer term Interseismic that I'll show you later this afternoon. But the workflow that we use is roughly the same. We've got our observational data set. So that's our radar, these fringes of earthquake deformation pattern contour maps. So we sometimes add in some GPS data if we've got that, and seismological information as well, because this tells us a lot about space. How has the Earth deformed in space? Seismometers tell you a lot about the time rupture history of an event. So combining them together usually provides you with more complementary information. And what we want to do is put that through a modeling approach where we say, how much into the earth has that fault slipped? Where did it slip? Where didn't it? Because where it doesn't slip is pretty much as important as where it does. Constrain these models that all have assumptions in them. They all have trade-offs in them. With surface observations and ground truthing, you usually want to ground truth any models that you have because you should never believe models. Everyone knows that models are wrong. So they need some grounding in reality as well from independent sources. But we can try and characterize the segmentation of ruptures, their slip to length ratios, lots of different proxies and metrics that we might want for this. And then we want to make use of that modeling approach and those data to interpret the way the Earth works. So as I said, what's uplifting basins and mountains? How are faults propagating and folding the stratigraphy? How is the stress being redistributed on the network of faults that might release stress here, but increase the stress on adjacent long strike faults that might rupture in either aftershocks or future main shock events? So, as I said, InSAR's been going for quite a long time, built up a large number of these contour maps of deformation for hundreds of earthquakes now. It was done painfully slow in the early periods. Now with Sensor 1 since 2014, it's much more systematic. And John, who will be leading the next sort of session as well, painstakingly to really automate this rather than doing it manually, build up a huge number. But authors recently have been compiling as much of these events globally, tabulating, cataloging. By building up these data sets, you can start to interpret, looking for patterns in their behavior. Pretty much how seismology did it decades before. The kind of number of earthquakes you can't capture, InSAR does not do underwater, so it's a big limitation. It's only useful on land. Fortunately, people live on land, so there's a useful intersection there of the hazard and the exposure. But the kind of numbers you expect per year for some of the small events that are just about detectable by InSAR is in the tens. And then obviously these sort of big nasty ones that happen along the edge of subduction zones are fortunately much lower rates. So we're not seeing anywhere near as much as the seismological catalogs can image, but we get a richness of the surface behavior that then lets you tie in with the geomorphology and geology a lot more. Now, there's a real detection limit, not just underwater problem, but also how deep and how small. So these graphs are trying to show you the limit of sort of detectability in terms of the number of centimeters of deformation you expect at the surface, the peak. Can't really detect it if it's much more than this without a lot more effort. But the bigger an earthquake, the easier it is to see. The shallower the earthquake is, the easier it is to see. So it's quite sensible ideas. The Earth acts as an elastic lid. It's a filter. You bury something deep, anything that goes on is filtered over a long wavelength and attenuated in terms of its displacement. So you want it shallow. If it's small, it's got to be really shallow. But as you're pushing these limits, you do get around this sort of, you do get the odd example of earthquake events that shallow. So here's one of those events that was done in Iran, one of the smallest ones that was at the time at 5.3. So this you'll be getting used to is some data, a blob, a bullseye, we normally call it. Earthquake happened here. So immediately one of the good things about seismology is you know it's there, whereas the seismology might have quite a bit of uncertainty around it. Have to downsample it, I'll come back to that. We have too much data to work with, so you always have to downsample it. But you model that and then you say, how well have I done? That's your literature over here. And from that, you get fault parameters. Where in the world did it happen? How deep did it happen? And then the orientation of that fault plane in space, which is obviously useful to us. So that's where it is in southwest Iran and the Zagros. So these are quite good. You can process over really hundreds of kilometers. You can sort of pick out these sort of signals relatively easily. So we've got an automatic system that does this, the COMET InSAR portal. So if for the very few of you that actually might be directly interested in modeling this sort of data, or at least just seeing where these earthquakes happen, what kind of patterns, each time there's a magnitude 5.5 plus event that occurs, it goes into this database. The data gets processed and put on this portal and then is available for downloading. So if I show you an example from last year, was it? Earlier this year. This is on the Chinese-Kyrgyzstan border. So the southern Tian Shan, quite a big earthquake, magnitude 7, not bad for the continents. This is the deformation pattern. Our portal shows you where the seismological representative was, the various frames of data that we have, and then one of the interferograms showing you we've got it. You can then go and download that information. Hope that link works. and work with that data in pretty much the same as some of our colleagues do. So want to make sure you're understanding what all those contour maps are. Here's just a simple picture of earthquake deformation. Earth cross, Earth surface, satellite goes over, radar, 5.6 centimeters in this case, imaging, Earth deforms in an earthquake, radar, satellite system comes back. The extra phase return path of the radar propagation microwave through the Earth's atmosphere gives you a path length, path range increase. And all those fringes are showing you in those interferograms is a contour map of how much something's gone up or down. So you just have to interpret them as how much, counting in, just as you would on the topographic map, the old style contours, how much deformation is. But instead of, say, 10 meters of height or 50 meters of height you expect on a contour map, these tend to be like centimeter scale kind of displacements. So we take an important earthquake, the Haiti 2010. This is an ALOS satellite image now. These bullseye patterns, what was important here was that the city where a large number of people were killed were Port-au-Prince here to the east. This was able to image the earthquake that did that, and it was actually outside the city. So the concern is the propagation to the west that has happened and to the east of ongoing earthquake ruptures that might happen here. But in this case, it happened there. You can use this to model the fault. But the first thing you have to do is what's called unwrap the data. So you look for where there's no deformation, you call that 0, and you just count those contours in. You multiply by whatever contour interval you've done. So earlier on, we just used to use the wavelength or half wavelength. But you build up to 60 centimeters of motion towards the satellite, 12 away. So it's just a counting exercise, and that's called unwrapping. A long time ago, that was done manually. You just draw contours. Obviously, nowadays, you don't need to do that, and there are things called unwrappers that will do that for you. Now, one of the important things about radar is it has to be sideward looking. It has a line of sight to it. So it's not measuring a vertical or a horizontal, it's measuring a line of sight. So if these are your plane wave propagation, normal to those waves is the range change direction. But the ground may move by some vector u in any direction and give you that same range. So in this case, the mountain moves towards the satellite. The satellite moves towards the satellite by a wavelength. It's the same as if that ground, the mountain moved up by slightly more than a wavelength. It gives you the same range change. Or it has to move twice as much as the wavelength, or more, nearly 3 times, horizontally to give you the same range change. It's moved one wavelength towards the satellite. So we have this ambiguity. We don't have enough information to know whether it went up or sideways. We just know how much closer or further away from the satellite it got. So what you have to do is usually combine information together. Now, Center 1 changed how much we could image these earthquakes by being much more systematic in its acquisitions, much more regular in it. So it has a high temporal coverage, and it does it at a fairly good spatial resolution of tens of meters. So that was in 2014. It really shifted. This was an earthquake. We did the Napa Valley. It was pretty much one of the first earthquakes that occurred. It was in Northern California. Fortunately, largely involved destruction of wine bottles rather than loss of huge numbers of human lives. But it was the first image that we sort of had to use and work on this event. Now, just to give you a repetition of what you might have had a bit before, but with an example of an earthquake, we're dealing with Sentinel 1. It acquires in lots of different modes, but our sort of standard one is the interferometric wide swap mode. So the data ships are sort of 250 kilometers wide. So it gives us, captures most large earthquakes in one take. So that's quite useful. In the past, they used to be 70 kilometers, and you would have to stitch loads of them together to get some of the biggest ruptures that might have been 400 kilometers long. It, as I said, it doesn't look vertically. It looks off to the side at a range of angles from about 25 to 45. It's unsynchronous, so always images at the same time of day. Polar orbiting, so it goes north to south, but looks sideways. So it means it's better at seeing east, west, and up, down. Can't really see north-south deformation. And it repeats every 12 days. So when there was a pair of satellites, you might get an image every 6 days. At the moment, it's every 12 days at best until Sentinel-1C gets launched. And the way it's acquired is something called TOPS mode, but it's basically does it in progressive scans of about 20 kilometers long. It's radar imaging. This is the sort of intensity image that you get out. Does it in 20 kilometer long strips, and then those have to be stitched together. And it's various sort of background processing that does that automatically. It does it on 3 subswaths. So here you can see the classic sort of radar picture. It doesn't look like an optical imagery. So if you start to get used to radar imagery as opposed to optical, mountains don't look right. Because it's looking to the side, one side, the bright side that faces the satellite, so it must be over here, gets most of the radar energy back, but it's what's called is foreshortened. And you get to a point where you get something called layover, but it's narrower than it should be. On the back side of the mountain, they look really wide because the waves that are intercepting them are actually stretched out because the angle of the mountain means those waves intersect much more widely spaced apart. So whereas rugged terrain, they look really quite different compared to a flat area, to look a bit more like an optical image. So you can see a city down here with bright intensity due to the urban structure, the urban fabric of the area. So that's really bright there, bright lines of roads, cities, and then darker areas of rivers that don't reflect the radar, bright mountains that reflect it back, dark lakes up here. So you stitch those all together. This is the Tibetan Plateau in the north, the Himalayas, the Kathmandu Valley, and then the north sort of Ganges down here. This is what it looks like in a Google Earth sort of red, green, blue equivalent image. So this is Kathmandu, it's the Tibetan Plateau, the mountains. So you can see they look very different. So you have to spend quite a bit of time if you work with this imagery, if you wanted to interpret it. And some of the latest commercial satellite data, say from my side, is really extreme in this. It does take a bit of effort to project that back in your mind. So often needs geocoded to make them much more easier to understand. Something called radar terrain corrected to get rid of this brightness, darkness, to account for the slope. So the things post-processing you can do to make it look like a more interpretable image if you wanted to as well. So just zooming in on one of those bits, I'm going to show you the topside interferometry, which is worked through. This is what you get when you do the interferometric process. Early on, there was huge problems with these burst discontinuities. You can see these 20-kilometer wide chips that you get these discontinuities in the data because you had to really match the data well together. So you had to do this enhanced spectral diversity method, which shifted the 2 images so they overlap perfectly to within 1,000th of a pixel, which is no mean feat, that they then interfere correctly, and you can build up this pattern. And as you increase the number of steps you do to enhance that, you can see that it becomes a bit more coherent. This is sort of small offsets you have to do to it. You can actually start to see the pattern of the earthquakes is a bit clearer, and you don't get those stripes out here where there's no deformation. So the take home from this, though, is earthquake here, counting the fringes, peak deformation there, where you see that bullseye faintly coming out, and nothing much going on here except probably water-related substance and uplift. So one of the key steps I said was about the phase unwrapping. So, this is coherence first, but I'll step over that. This is the filtered data, and you want to unwrap from somewhere that's about 0 to this peak deformation. So this has now been flipped and geocoded. So again, one of the big steps is to go from the radar geometry, which is sideways looking, and is in range and azimuth, into a geocoded lat long or UTM reference frame. So this has been geocoded and then unwrapped, and you can change the contour intervals. So this is now 10 centimeters instead of an arbitrary wavelength 2.8, something a bit more interpretable, or you do the full unwrapping to get the full displacement from 0 to 1.5 or 2 meters of displacement. This was the Gorka earthquake that happened near Kathmandu, 2015. Now, there are other techniques as well that you can extend. We've got what I showed you now is conventional InSAR, so the interferometric phase portion. You can, for big displacements, use other techniques as well, such as the range offsets, so you're actually pixel tracking some of the data. Azimuth tends to be a bit noisier because the resolution of those cells is a lot quarter. And you can use something called MIA, multiple aperture InSAR as well. So these just give you different views of the same earthquake that have limitations and noise, but in this case, they get you nearer the fault. They don't saturate in the same sort of ways, akin to seismology. Here we lose correlation in the near field. The ground shaking is too intense. The gradients of phase are too large. These techniques preserve that offset. So that's much more useful for interpreting actually where the knife cut of the fault is. Here it's sort of hidden in the loss of data. And then there's the different satellites you can use. So previously that's different techniques, different satellites have different strengths and weaknesses. Here's ERS of the Izmit earthquake, Emirates the deadly BAM earthquake in 2005. So these are European Space Agency C-band missions, so their wavelengths at 5.6 centimeters. Also got RadarSat-2, so Canadian more commercial platform. ALOS L-band, so much longer wavelength, so this works well in Myanmar, where it's much denser vegetation. The C-band doesn't do very well. L-band, 24 centimeters, does well with leaves, trees, plants, can cope with that better than the others. X-band, very high resolution, just a few centimeters in wavelength, but their resolution cells are a lot tighter as well. So that's good for certain targets, volcanoes, for urban areas as well. So one of the things to hit back home is this line of sight. It's not vertical, so you have to take into account which way the satellite is going and which direction it's looking. So that's its azimuth, which way it's flying, south to north, say, for polar ascending, and its incidence, what degrees off of the vertical, off in the nadir it's looking. So this is a picture of the Zagros Mountains of Iran out towards Iraq. And the question is, can you spot where the earthquakes happen? This is now the phase. Where's the earthquake? Everyone happy? Yeah, you're looking for bullseyes. Hopefully you're pointing that. Yeah. So that, there are other long wavelength noise here. Higher frequency interference of atmospheric patterns probably over here, but this is the kind of bullseye. And hopefully you can start with an eye of faith, and having looked at these enough, see a secondary one there as well. This requires a lot more, working with the data, but this one's a bit more obvious. And it's an asymmetric load pattern that you often get with earthquakes, particularly dipstick ones that you'll be able to explore in the modeling section. But when you're looking at it, as I said, in the near range, the incident angles are a bit nearer vertical, so about 30 degrees, and about equal 45, 46 degrees in the far range. So near to far range, you have different sensitivities. This can measure vertical and east-west equally well. This one is obviously more sensitive to vertical and less sensitive to horizontal because it's looking slightly more down. So you have to take account for that. Where is the earthquake in it? The azimuth at most latitudes doesn't change much. It's heading almost north. So that, you can usually use an average. But a lot of software will give you the unit vectors, east, north, up. So on our website, we have the unit vectors that you need that conveys these two bits of information about which direction in east, north, up space that the radar's pointing. But what you will need to get used to if you are interpreting these earthquakes is that they will look different then. So here's a synthetic example of an earthquake. Depending if the earthquake's flying north to south and looking right, or north to south looking left, you can see the patterns change. And they can change quite markedly depending on which way it's going. Now, this is good and bad. It means you have to interpret it differently, or you'll have to have your modeling software capable of taking in these unit vectors. But it also means if you do have a range of observations, you actually can constrain the problem better. As I said, there was an ambiguity. If you've only got one look direction, you don't know whether it went up and up or it went sideways a lot. So if you've got this and they are in opposite directions, you can actually tell it's gone up if they're the same time, and then gone sideways if they're opposite sides. So that sort of rule of thumb. So having more observations enables you to constrain. And really, notionally, you need at least 3 independent observations if you want to constrain it in 3 dimensions or 3 components. Also, for those of you who haven't done tectonics, geology, geophysics, I just need to convey for the practical the different kinds of faulting that you get. So the Earth can behave in a strike slip mode where the crust moves laterally. So here we have a lateral strike slip. So a line of trees gets offset. That's often seen at San Andreas, big transform continental fault, but actually the ocean transforms as well. And throughout conjugate strike slip systems that you see. So that's one style of faulting, largely horizontal. The beach rules that we use in seismology that represent that are shown like this. They just show you the polarity of the seismic waves and the plane, the fault plane, auxiliary plane, the 2 nodal planes that are represented if you do seismology. but it's a representation of the motion in that event. Now we move to not the strike slip, but the dip slips, of which there's a normal faulting event. So when things large, you go down. And this happens at mid-ocean ridges in the oceans. You can't see that, so we have less interest in that. But in areas that are extending, such as the Tibetan Plateau, Greece, Turkey, where you're pulling apart the Earth's crust, it's collapsing perhaps under its own weight, and you get extension. So that's normal faulting. Reverse faulting, that's largely manifested by subduction zones where you get huge megathrust earthquakes. But anywhere where you've got continental collision, you're uplifting materials, you shorten the crust. So you're going to get a lot of vertical in motion in these dip slips. So that's the pattern of earthquakes. You can see that there's quite a contrast to the oceans, rigid aseismic plates with very little earthquakes in it. Edges of those are delineated here. That's your classic plate tectonic paradigm. Is why it was more easy to understand that they're not there, rigid, aseismic, and then deformation at its edges. Continents are much more diffuse. They're older on average. They've got much more inherited fabric, and the patterns of earthquakes are really quite diffuse. And that's why they've been a bit more of a challenge to understand. If everything was lined up, you would know where the earthquake's going to be in a line sense, not in a 2D sense, whereas here they could be anywhere. Okay, they're really quite broadly distributed. So we're trying to understand the pattern of strain across this continental area. And we can model these events using simple elastic deformation and dislocation theory. So they may look complicated, and there's a lot of noise in here. There is a bit of complexity from the way the Earth broke. But if you imagine it's just an elastic band that you pull and then snap, it's pretty much analogous to that. So the behavior you can say that happens along this fault here, say the isthmic fault, is that the Earth doesn't do much in the far field, and as you move into the near field, it bends, it snaps, it's an elastic medium. So similarly with these dip slip earthquakes, the difference here is strike slip tend to be symmetrical, so they bend in a symmetrical sense around the fault. Dip slips tend to have an asymmetry. They have a wall here, the hanging wall uplift of this thrust fault in Iran is much larger than the footwall substance. So here you've got two lobes of deformation, one big, one small. Similarly, in this event in Turkey, you've got hanging wall substance here. Footwall uplift, you've raised the mountains a little bit, but you've subsided the basins a lot, built a lot of accommodation space there. So there's that asymmetry. But it is just like you're breaking an elastic medium to do that. And one of the things we're trying to get from the geodetic solutions is a measure of how big they are, compare that to seismology that has the seismic moment. We can get at this from the moment magnitude. We need to know some parameters about faults. That's what you will do in this practical. Basically, how big is it? So we need length, how long is it, and how wide is it? It's down, dip, width. Then if we know how rigid the material is, we can actually say quite simply, how big is it? The moment is just how rigid it is times how big an area it's moving, so the area of width, and how much slip. So if you remember your sort of classic pushing a block along a table, you need some sort of measure. It's a bit like that, the work done against friction, but it's the displacement that matters, the area of which is work. That's how much energy is released. We also can use some simplifying ideas about the way the world works. A long fault can have more slip on it than an earthquake, and more slip that happens the longer the faults get. It's sort of central things. You can't have a huge amount of slip on a tiny fault. It's nonsensical, but it's also not possible from the material science side of things. So we can use scaling relationships that say, if something is about 10 kilometers long, it might have moved a meter. So that's the slip to length ratio. You can use those back of the envelopes to help constrain what you expect. Small earthquakes tend to be equidimensional. They might be circular cracks, they might be square, but you can approximate that the length is roughly the width. So these are all back of the envelope. As they get bigger, the Earth's seismogenic thickness sort of saturates at maybe 15 kilometers, and they tend to get longer, or they involve more segments that rupture along strike. But to start with the small ones, they're roughly the same shape. Now, you can always make it more complicated. Any model, always you want to add complexity if it's warranted. And all you have to ask yourself is, did I learn a bit more about the way the world works, or did I understand my model a little bit less? So as long as you've got an information gain, you could make these things more complicated. But you should always start with the most parsimonious, reductionist approach to it. What's the simplest model, the fewest number of parameters I can use to explain my data, my phenomena? And then you can convert these moments once you've got this, just using the moment magnitude relationship. So if you do seismology, you do this all the time, just so that you can put it on the magnitude scale. So the way we describe faults, again, for those of you that aren't sort of field geologists, is with its geometric terms. Those were its dimensions. Now it's its strike, dip, and rate. So it's the orientation of the fault in space. Here's an example from Greece of a limestone fault covered with alluvium that's been exposed in a quarry. You see a beautifully polished face there. That's the fault. 100 meters high in this case. It's hard to get the scale on there. But its strike is which direction is that fault plane projected. So that's the compass direction that way. Its dip is how steep it is from the horizontal down. So this is pretty steep. The photo exaggerates it a bit. And then how is it ruptured? So the direction in which the hanging wall above it, whatever the block was here, slipped down there. So it's not a landslide, it's a fault, but you can imagine it's sort of similar. It didn't go vertically down, it actually went up to the side. So it's not a landslide gravitational collapse. These are cross faults, so they don't have to go pure vertical. This has a rake on it that isn't perfectly normal. So that would be off 90, well, minus 90 degrees, not completely normal. It has what's called a small strike slip component. So those are other parameters you want to know. Apart from where is it, that long, how deep is it, how big is it, length, width, is its strike, dip, and rake. And with all those sort of terms, we can understand something about it. And then we can compare it to the seismic information of hypercenter, epicenter, centroid depth. Those come from the seismology. We can't do anything in time. We can only do the bits in space. So the data sets are complementary. And as I said, you can model these as elastic dislocation. So this was formulated in 1985. We call it the Okada model. It's our stable underlying approach to understanding how an interface moves in 3 components. But basically, we want to get at sort of these 10 parameters. Where is it, and how is it orientated, and in what direction did it move? As I said, we have to input our data into our models, and we usually have too much data. If you've got 1 billion data points, you have to ask, do you have more information? And actually, you only need thousands of data points to constrain 9 parameters usually. You're only solving for 9 things. You don't need much to be able to do that. So InSAR measures every 10 to 20 meters. You don't need that. You often have to downsample it. Sometimes you have to downsample it sensibly and maybe have more information where more is happening. So here in this case, the data for this earthquake in Tajikistan, we heavily downsample in the far field where there's not much going on except noise. So it carries some information. It tells you nothing happened, which, as I say, is just as important as something happened here. But you maybe densify your sampling here if you want to look at how the slip changes along the fault strike. Here's our model, as I say, from that Okada model, and we've segmented it into 4 bits, but we say how well does our model fit our data in terms of a residual and our misfit there. And as you can see, it tends to fit it pretty well, and all you're left with is noise. And you often have to ask yourself, by adding more parameters, does this change? Because if you add more parameters, you might reduce a bit of the residual on it. You know, for the extra information you have there, is it warranted? And as you get to bigger earthquakes, I said it's not just a simple square or circular rupture, you actually get segmentation. So seismology tells you something here. Here's the aftershock clouds. It's in New Zealand, so it's done quite densely. You can start to join all the dots. In this example, the earthquake Darfield was the main shock. Christchurch happened a few months later. But you can start to join the dots and look at where the fault segments maybe are. And as seismology gets better and better, it is more and more possible to really localize the fault interfaces to do this, depending where you are in the world. But with the InSAR as well, it gives you that richness of information. And you can start to say, well, it looks like there's something there. It looks like there's something along there. And hopefully with your eye, and then there's another vent in here, and nothing in between in the radar. There's plenty of aftershocks, but there's nothing in the radar. So using those 2 data sets together is very powerful. But this is the segmentation I got with the InSAR, and it seems to line up pretty well with where the aftershocks are, but there are big differences there. This one is okay because actually it's a dip slip, so this is all projected down there. But over here, we get 2 faults in the InSAR, which then we can start to interpret the seismology, but also this gap now. nothing much happened in terms of displacement, but there's certainly a lot going on in aftershock. So the argument is there a through-going structure there that joins up all these segments? So that's important for understanding the hazard in these regions. Also, it's not just a segmentation along strike, it's a segmentation with depth. Here's an example of two earthquakes that happened one above the other. This is MSAT data from northeast Tibetan Plateau. First earthquake and the second earthquake were the same magnitude, but do they look the same? This one only has a couple of fringes, this one has many. So this one is shallower because it's the same magnitude, but it must be nearer the Earth's surface if it's displaced it more. This one is buried deeper. So one of the hypotheses is one is shallow in the crust, one is deeper in the crust. And how are they related to each other? Similarly, in this one, earthquake from Van, dip-slip event, thrust in the mountains here by Lake Van. What's important for this is these fringes are all closed. These are all closed fringes, so that tells you they're buried. As they get tighter and tighter, they actually get nearer the surface. But in this case, what the modelling told us was that there's no slip above 10 kilometers. All the slip was really quite deep, 10 to 20 kilometers down. But this fault is at the surface. It did actually move like just a centimetre. So there's clearly a through-going fault. This busted the lower bit, but it didn't break all the way through. This one did. It broke deep then shallow. This one did. They're just individual examples, but it does mean you would be very worried now that this part of the fault needs to go. This has slipped. It builds up pressure, stress on this bit of the fault. It's got to go, and it's probably going to go seismically, not aseismically. There is some aseismic creep, but you would want to know that it was going to be released entirely. Now, it's not done anything in 13 years, but that's the problem with the earthquake cycles. They're not short, they're really quite long, hundreds of years, which is why they've been so hard to understand. So this is just showing you then for your modeling how you're going to, oh yeah, it doesn't animate. Oh, this is in the browser. This should be an animation showing what happens as the fault gets deeper. But basically these peaks get shallower as the fault gets deeper. The amplitude of the displacement as the fault is buried gets smaller and the wavelength gets longer. So if I just show you the static image, this is a very shallow event, lots of fringes. So when you start to do the practical, it's either big or shallow. As it starts to go deeper, these fringes get more widely spaced. They start to get further out a bit, so it's widening. And then when it's really deep, you actually lose that secondary lobe. You can barely detect it amongst the noise. And then you get really quite a long wavelength pattern. So you're looking for changes when you're modeling, when you're saying how deep is this event, for instance, changing the amplitude, the wavelength, and that gradient, how tight those fringes are. Those are your diagnostics. And you're going to do a little trial and error like this. I'll try it a bit deeper, I'll try it a bit shallower, compare the model to my data and see what the misfit is. That's the exercise. There are other things when you move on to more complicated ways of looking at this. Those are what are called uniform slip models. You just assume a rectangle that has the same slip on all of it. You can make it very complicated. I said as long as you can justify making it complicated, do so. But you need probably independent information, aftershock clouds, fault slips from geologists measuring surface displacement, something else that constrains your model. But all these models need something called regularization. And what that means is some sort of smoothing or penalty, some cost when you do the inverse model to say, where do I put slip and where don't I? So any model actually wants to put unrealistically high slip very, really deeply. So this is 20 meters of slip really deep down on a concentrated patch and not much elsewhere. But that's not really how we think the world works. It isn't all slip and no slip. But because we've only got surface observations, we're not measuring the slip on the fault, we're measuring the displacement at the surface, not underground. These are the trade-offs in the modeling. So you have to do something like this regularization, which is called basically, in this case, spatial smoothing. And the more you smooth it, the more it sort of becomes those rectangular patches. So there's that trade-off between taking a simple model or a complicated model with assumptions and trade-offs. And there's also that resolution problem. As I said, we measure stuff at the surface, so surface here, and we can do a simple test, what's called checkerboard test. It's often done in seismic tomography. We put in a known model, and you should do this with all your modeling approaches. Put in something you know, put it through your workflow, your inverse problem, and see what you get about how. So then you know, I put that in, I got that back out. You know, it's barely right at the surface in the upper 2 kilometers. But it makes sense. 2 kilometer patches, you can only resolve in the upper 2 kilometers of the Earth. It's sort of scale, it's a length scale. But if you want to resolve something at depth, you can really only say that bit's slipping, that's not slipping at 9 kilometer wavelength when you're that deep. So that's sort of hopefully fairly intuitive to you. But what you don't want to overdo is overinterpret patterns down here because you just can't resolve them at a 2 kilometer wavelength. You can only resolve them at a light extent. And then just to finish with a couple more examples, this is from Iran, the radar sat image I showed you, the contour map, and then what's been unwrapped. A lot of data in the vegetated areas. This is the incoherent areas. But we've got enough information to constrain the fault. There are 2 lobes, there's one up here, one down there, so that's the segmented rupture. They're getting quite tight, so it means it must be getting relatively close to the surface, but they're not discontinuities, so it probably didn't quite make it all the way to the surface. This is the whereabout anticlines, the salt dye appears in the middle. These are the 2 thrust faults that ruptured in the surface, and this is that distributed model. So one of the things we can take home from this again is where in depth did this slip occur. In the northern segment, it occurred quite deep. In the southern segment, it jumped in the rupture and got a lot shallower. Not all the way to the surface, but a lot shallower, a lot smaller. So there's that sort of cut-off between them. And you can start to ask questions, why is that? You can look at spatial patterns of incision rates, look at where these faults are uplifting and bending these anticlines. But you can start to look at where these detachment horizons are. There's the Hormuz salt, which is a barrier, and it's quite a mobile layer. Salt migrates over geological time, so it probably doesn't allow stresses to build up as easily. But you can sort of compare where those were slipping and actually get these detachment horizons which stop the fault and compartmentalize it into deep and shallow. So the Hormuz salt stops it going any deeper, and actually in this case, those shales break the crust into 2 halves there, an upper and lower bit. So I've sort of mentioned the modeling aspect. The forward problem is to say, given my earthquake, strike dip break, what do I predict the ground would do? So that's what you should do straight away. Is I think something happened. So the seismology says an earthquake's happened. Try and predict what the satellite should see, because the satellite may take a week to give you some information. You know straight away what you're expecting and where you might be expecting. What's harder is called the inverse problem, where you've got your data with some of its noise, and you want to say, given my data, what are my fault parameters? What's my fault orientation? What is my fault set? And that's a bit harder to do. That's a slower problem. This is a fast problem. From 9 parameters predict data. From this, from data predicting what the 9 parameters are. And there are different softwares that have been developed here, and then there's lots of others available to you now from the open source community. One of those is something called GBIS, which if you enjoy some of the simple fault models today, you could go on and download to do a slightly different inverse problem. This is called a Bayesian approach. But this very much formalizes what you'd say in terms of, given my data and my estimate of how noisy it is, what are the likelihoods of my fault being this certain strike dip and rate? So not only do you get a solution, you get an estimate of the spread of possible solutions. That's what's most useful about the Bayesian approach. It gets the uncertainties, because as I said, all models are wrong, and you don't want to treat your answer as the answer. If you know a number, a parameter, it's largely meaningless unless you know how poorly you've known that parameter. So knowing a strike at 180 degrees isn't very useful if you don't know it's plus or minus 10 degrees. You really need some measure of uncertainty on it. Otherwise, someone can't then use that and weight it correctly against their observations. So that's for uniform slip. If you then want to take distributed slip, there's something called Slippery, which is also developed by a colleague here. And in this case, you've got more patches to play with, but instead of doing that smoothing approach that I said was spatial smoothing, which is this right-hand one, you can try and take a more sort of realistic approach to how fault roughness might be, and that's called the von Karman approach. So trying to be a little bit more realistic than just smoothing out the high slip. So hopefully in summary there, we've given you an insight into that the InSAR, under certain caveats, can be useful in complementing seismological catalogues. It gives you a much greater richness in the near field, but has limitations about where it can be used. An increasing number of earthquakes have been done now. So instead of individual case studies, catalogues are being created. So it means you can start to do more statistical approaches to these. And it's useful for the large or shallow continental earthquake. So we want to show that you can use these case studies, though, to understand how you might grow individual structures like anticlines, faults, and folds, how it might lead to long-term growth and mountains, and stuff like that. But as I said, there are real limitations to this. You're only measuring the Earth's surface. So if you want to measure an earthquake at 500 kilometers, and they do exist, you're not going to hope of being able to do that with InSAR. We recently published a paper where we pushed that to just over 100 kilometers, but that's really pushing what you can do with it, and it has to be really big. As I showed you that trade-off, only big earthquakes. And we've got modeling codes available in other research groups around the world that enable you to do this. They've all got a bit of activation energy to use. You do have to work quite hard to get some of them going, and you have to understand the underlying assumptions that go into it and be really careful, but they are freely available in those papers that sort of explain what they do should you want to do that. So in terms of practical class, this is what we'll do in the next session. This was developed by one of my PhD students, Andrew Watson here. So it's a jupyter notebook to work through the 4 models to COMET. And John, you'll be sort of doing an introduction. Is it straight after this? If we just do the Q&A and then we go straight, there's no break. We don't give breaks here, do we? Sorry about that. But that's what we'll move on to. Will you go through this sort of stuff, John?
Yeah, I'm just going to introduce it.
Yeah.
Practically, yeah. But I mean, yeah.
Okay, just briefly then, I mentioned these are the 9 or so parameters you want. Where is it? How is it orientated? How big is it? So you'll be going for that. That's at the beginning of the Jupyter notebook. Reiteration of what we mean by the fault planes, that dip and the vertical. Please ask us if some of this terminology, the rake, is a bit confusing. So that's fault in Greece I showed you. This is the incremental slip that happens there, so those striations. The strike is in that direction. The dip you can't see. The rake is that angle around from the strike that shows you what direction. So it's always a bit complicated if you've not worked with rake before. And then this is the modeling software that John will lead you through. You input those 9 parameters on the left. Okay, there's some starting values here, and the model does its business, the carded dislocation. But what we're looking at here is the east displacement, the north displacement, and the vertical, because this fault here did something, it moved, it slipped. Okay, so that's what we see. And then the 3-dimensional displacement, you get that these vectors. And then I think there should be examples of what that looks like when the satellite views it from a single line of sight. Because as I said, it does not measure east, north, up, it measures a line of sight. So that's what we see here. So you've got these are hard coded in. -10 is the same as 350, it's facing north-south. And you have those, what I told you about, the wrapped fringes, the contours, like a hill, and then the unwrapped that gives you the total displacement. These are all contour intervals with a few radians or centimeters. This is the total amount of displacement you get, and that asymmetry. Most of the motion has happened in the hang wall over here. I think that's the end of them. So there's just a few of our earthquakes that have happened over the past sort of few years that are in the catalogue. We've given you those as examples to do. I think, yeah, we've got a few of those. So I'll leave it there and just ask for some questions then if you've got anything from the audience, and if there's some lined up for the Q&A, Milan. But anything that you want to ask now, we'll be here to obviously walk around and ask them as well. Anything you'd like to raise? Okay, we can share the link to the earthquake data after. That information is, yes, we can definitely share with you the link that I put on there to the portal. How reliable is InSAR to analyze faults in the north-south direction? So that's a good question. If you put this fault instead of east-west, north-south, it's not the orientation of the fault that matters, it's the displacement. So if all the motion is north-south, so if you imagine actually an east-west thrust fault, most of the motion is north-south in that event, then it's not reliable at measuring that. It's not as sensitive, so the noise saturates it sooner. It's not a pure north-south, so if you've got descending, that's 190 degrees, ascending 350, you've got some sensitivity north-south. It's just much less than the east-west. So there is some information in there. Future missions will try and do a long track information, so Harmony should be better at that in the future to give us that third dimension, that third component that we desperately need to really reduce the trade-offs. Basically what happens in fault modeling, because you know the north-south less well, you will trade off the strike and the rake and the dip. You tend to trade off the parameters. If you don't know it so well, the model can't constrain it. And hopefully a Bayesian approach should tell you when there are those trade-offs. That's the advantage of using it. Yes, so is it possible to distinguish different types of earthquakes with InSAR? Hopefully with the modeling you can do here, it's going to be quite clear you really easily can. That a strike slip earthquake looks very different from a dip slip. And a thrust, because it mainly uplifts, and a normal fault, because it mainly subsides, will look very different. So it's definitely very good at discriminating between types of faulting mechanisms. As I say, the rake's one of the dodgy ones. So whether it's pure normal or slightly off pure normal gets a bit harder. But pure normal, pure thrust, you can definitely resolve as long as you don't make the classic mistake, which is the sort of sign change. So one of the big problems we have in radar is a range change is positive away, but in GPS up is sort of conventionally positive. And those two things have been conflated quite a bit, because for us, if something went up, its range change decreases. So it was originally taken as negative. So be exceedingly careful about your conventions, about what's away, what's towards, what's positive, what's negative. And is it in radians, which means it's got something to do with the wavelength, the phase change, you need to convert with the wavelength, or is it in centimeters, millimeters? Those are the big things that sort of trip everyone up. God, I can move fast now. In general, what is the maximum depth of earthquake? So as I said, we got down to 100 kilometers with a magnitude almost 7, I think, so it's pushing it around about 7. But you know, you can measure 6s if they're in the upper 10 kilometers. There's that trade-off with depth and magnitude. But you can do it. Magnitude 8, you could go a bit deeper, so beneath South America, Peru, you can measure magnitude 8, but you have to basically image the whole of the South American continent pretty much, because once it gets really deep, as I showed you, the displacement is really quite wide. So you need lots of InSAR data to cover that. Just to be clear, is there a minimum magnitude and depth? Not really, because we're finding smaller and smaller ones. So magnitude 4 is probably the smallest, isn't it, John? 4.3. 4.3. Yeah. So don't go looking for magnitude 2s. Though I know there are more of them in terms of the Gutenberg distribution. You won't find it. It'll be something else if you think there is. You're not going to measure most magnitude 4s. They're too deep. But ones that are related to unloading or coring might, you know, I think in south of France there was one that was an example like that. How to determine the area that could be affected by an earthquake? If it's an earthquake co-seismic, you are measuring the area that's affected by the static displacement. It's not the same as the ground shaking, though. The InSAR measures how much is the static change. So if it's moved a centimetre, but it doesn't tell you how much the shaking was in the earthquake. You need strong motion seismometry to do that, and that's much more useful in terms of the earthquake hazard. You know, the co-seismic displacement is not an earthquake hazard. It's just a static displacement. It's how fast it happens and the shaking that goes along with it that matters. Do we need to apply the solid earth tide correction for earthquake analysis? So no, we normally don't. The bigger the earthquake, the more you would. So it's for a small pinpoint earthquake, solid earth tides happen over a very long wavelengths. For subduction zone events, it will be the cherry on the cake. It's always better to put in as much known corrections as you can that accurately capture just some of it. But it probably has a very small contribution. Ionospheric definitely does. In that earthquake we looked, that was very deep beneath Chile. In accounting for the ionospheric noise was important, so doing a correction for that. Doing corrections for atmosphere matter. We're trying to find small earthquakes, atmospheric corrections. Some things it's a signal to noise ratio problem, so you do want to do it. Accounting for topography might be important for some things as well, particularly around volcanoes or large things like the Himalayas. If there isn't any surface rupture, would you be able to say anything about the slip from InSAR? Yeah, that's a great question. So definitely yes, because those models can resolve some slip at depth. So even if it doesn't get all the way to the surface, we still tell you how much it's slipping at 1 kilometer. But as I said, with the caveat that it's less well resolved. So it's much more smooth. We don't know exactly, but we can tell you which bit has and hasn't to some degree. The uncertainties are just greater. If it's come all the way to the surface, it's really a lot easier. Plus, you can resolve what's called the focal plane ambiguity. In all these events, there's what's called the ambiguity. You don't know whether it's dipping that way or that way. And the deeper it goes, the more those two solutions look the same. It's the same in seismology. If it breaks to the surface over here, you know it was that one. And over here, you know it's that one. So it sort of breaks that symmetry of the problem when it breaks a free surface. Right, we better, are we going to say this is the last one? Is there any range determined by magnitude of shaking to measure the zone of earthquake effect to understand what area could be damaged? Yeah, so you have to move to other techniques to be able to understand the total area that's damaged. So there's coherence mapping. So I glossed over that. You did coherence this morning? Okay. So basically, if a building falls down, the InSAR loses coherence. And that's basically what some research groups have done around the world, is to, in that disaster risk management cycle I showed you, that's what you do immediately after the earthquake, to map out exactly the distribution of devastation across the city, is where does the InSAR lose its signal, and to what degree and how quickly. So that's one aspect that's done. Yes, so at the back.
So I've been staring at this for some time now, like this slide is up, and I thought, if you combine multiple observations to break from the line of sight to get a 3D displacement, those observations are also spaced in time. Does it ever turn into a problem that there's that they're not temporarily, like contemporary observations, like not all?
Yes, it really does actually.
Like in what situations do you run into that problem?
Yeah, we can InSAR any images every 12 or 30 days. If you have to wait, literally ascending gets done first, and 12 days later to descending. The big problem is the post-seismic slip that happens. So you can try and do some time series work, and a colleague did that for some earthquakes. There's a lot more effort where you're trying to solve for what might have evolved between those two. So if you had lots of images that happened over time, you could start to do a bit of it. I mean, we've basically in the past hoped the post-seismic is a small fraction of the post-seismic, and the throwaway statements that affect. It will vary from earthquake to earthquake how much the post-seismic contaminates the co-seismic signal you're after. Yes.
Into the future, sensor, for example, biomass with P-band can be used to measure like a deeper earthquake.
So it depends on the platform and how well it's orbitally controlled. So the wavefront doesn't sort of map in the same way. I think maybe you're thinking about how deep you can go. That deals mainly with how well you can deal with vegetation. So it would be about the same constraints on depth. Even though if P gets really longer, it doesn't mean you can go really deeper. It just means you can deal with loss of data due to vegetation better. But it does rely those satellites to do the InSAR. Basically, Sentinel has to be flown through a tube that's only a couple of 100 meters wide. So every time it goes round, it needs to be in roughly the same place when it takes the image. And if it's not orbitally controlled using a lot of fuel, which is currently what the problem is, it's not doing it right, then it becomes harder and harder to do the interferometry. And eventually, when what's called the baseline, when it comes back round and it's 1 kilometer away, you can't really do this approach. So yeah, it depends on the system whether it would work for InSAR, but it would have a similar sort of characteristic. Okay, right, should we move on to the modeling?
Okay. So thank you very much, John, and welcome another John.
Big John and Little John, let's just switch right now.
Yeah. It's from Robin Hood. Okay, just let me first find the link to share to the in-person participants. That will be, where do I have it? Okay, just a second. So the in-person participants can use again that Jupyter Hub that I shared before, please use the same username as you used before, unless it was not working. In such case, please raise your hand, and you will be able to find the Jupyter notebook in Day 2 COMET folder. Okay. Now, yeah, here is the link. I will probably just share with them the GitHub, and you can tell them which to run, because I don't know myself.
Either work.
Either work, I think. Okay, so I'll share the direct link then. So share it in the. So to online participants, please have a look to chat area, where you will find the working binder link. And just in case, I will send also the repository for this practical, and that's all from my side. You will need your own, right? So I will set it here, and I will probably just duplicate the I will duplicate the display, so it will be easier for you. So okay, fine. Share screen. Okay. Now, here, what's this item?
Thank you.
Yeah, yes.
Okay, I'll get started. So basically what we're going to be doing in this practical is having a go at what John has just described. So we're looking at the most parsimonious, the most simple, the easiest model that we can. We're not going to do any distributed slip or anything like that, but we're just going to represent an earthquake as a uniform slip using the Condon model. So we have a Jupyter notebook here, which I'm sure you've all been using before, but if there are any problems with the notebook, I'll come around and help out. Thing to note here is this COSeismic lib, which is in this this folder, has a load of really useful functions in. So if you don't take anything away from this practical, just take that Python script with you. It has the Condon model. It has all sorts of different things that are incredibly useful. So that's one to note. If you're going to do this in your own research, use that module. So key takeaways from the practical, we're going to be looking at forward modeling. So we want to know how earthquake fault parameters affect what we see on the surface as surface displacement. And then we want to understand how that looks in line of sight. So the line of sight concept that John was explaining, we're going to be converting from east, west, north, south, and up, down into a look direction. And then we can see how, when we edit the rake, the strike, the slip, the dip, what impact that's having on our line of sight and what we're actually seeing in the InSAR. So first of all, if we want to get started, so the other thing we'll be doing is starting to compare this against some real data to show you just how difficult it actually is as a forward model to try and fit a fault parameter to real data. So what we usually do is, well, what I do in my research is we use GBIS, which is that Bayesian inversion software that John said. We're going to be doing basically like a Bayesian inversion, but you guys are going to be the walkthrough. So I want to see how close you can get to the data just doing it manually. Talk amongst yourselves with the forward model. Talk amongst yourselves with what parameters you've got, and see if you can narrow in to the best solution possible. And then we'll see how your results compare against John's results. So yeah, try and get it better than him. That'd be good fun. Okay, so first of all, we need to just load in your modules, and we're going to define a grid in which to place our Condon model. So just run those two code blocks, and then the next one is where, oh, hang on. Okay, I don't seem to have. NumPy not have float. Oh,
If we're all having the same, by the way.
you're all having the same problem.
Yeah.
Okay.
It's because I don't know when I think they changed that somewhere in Python, like NumPy is float 32 or 64, like you have to specify what it is.
Yeah, but
So either it needs to be like you remove NumPy and just checking if it's float, because it's type checking somewhere in the code.
yeah.
I don't know which one to check.
Yeah, but that's actually in the that's in that module. Why is that not? Is Milan still here? Or is he? Where's Milan gone? Okay. Right. This was working earlier. Okay, I think it should work on the binder. It's got the wrong version of Python in here. John, would you mind going and get Milan? I'm not quite sure, because I don't quite know how to upload
But it worked
this.
with it this morning.
Yeah, so the binder one's always been working. I don't know whether it's just the wrong version of Python's been put on the
Okay.
workshop.
Was that from last week? This worked in the
Yeah.
comment work last week.
It's not. Yeah, I'm not sure. Yeah, I've only ever done it with binder. Can you guys in here launch the binder?
That wasn't working for me.
Wasn't working. Okay, excellent.
Is it working now?
Yeah, could you give it a try now? See if you could try on the. Have you got Andrew's Git?
Yeah, permissions to edit the code size of the files.
Well, yeah, no, I don't have permissions. Milan, right? Sorry, but the Python version on the workstation seems to be wrong. So I'm getting an error that the MP float isn't, so I need to edit the.
NumPy doesn't work or what?
So this is on the workstation. So NumPy, the NumPy version is wrong for COSeismic lib.
Yeah, so I'm reading it's NumPy 1.20 where they removed this, I changed it to the.
Yeah. So we should change it to from float to float 32. Yeah, okay. Where is that?
It's in COSeismic lib. It's in the.
So we cannot really. Yeah, there is no. Like we will need to edit that one, which we can do. Okay, so let's see if we can do it fast.
I don't know where that might.
Hmm. Yeah, okay. And that was the only thing, really. Okay, so but now you will need to restart the kernel.
Okay.
Yeah. Okay. Yeah. This change should affect everyone here. So now it should be working hopefully, but you will need to run from the beginning. So yeah. Okay.
That works for me now.
Mhm.
Yeah. No worries.
Okay.
Okay, perfect. Thanks, man. Excellent. That was great. Yeah, appreciate that. Okay, sorry about that brief hiccup. So first of all, we'll be using the card model to model a left lateral strike slip fault. So what I want you to try and understand is, so we've been looking at this on John's screen for a while, but I want you to try and understand why you're getting the displacement that you're seeing in each of your directions. So on here we have east-west. So we have the top portion moving eastwards, and the bottom portion moving westward, which makes sense for a strike slip. For your north displacement, what you have is material being sucked in here, coming southwards, and then being ejected here, going northwards. And the same the other way around, you have material coming in here northwards, positive, and being ejected out southwards, negative. So you end up with that classic sort of four-lobe look. And because of the same thing, you have uplift on one area, coming in from here, uplift, and then you have subsidence here. And the same way, the other way around, you have subsidence on the other side, followed by uplift. And if you look at the 3D sort of vector field, you can see that represented quite clearly. So with this sort of code block, what I want you to try and do is have a play around with the strike direction, see what effect that has. There's trade-offs, as John said, between depth and magnitude. So in this case, magnitude is proportional to the width and length of the fault. So see what impact that has on the displacement you're seeing. And what you're looking for is a change in wavelength or a change in which direction you're getting displacement in east, north, and vertical. So this will start to make sense when you try and combine all three of them into one look vector, and you'll understand kind of how each individual component of displacement affects what you see in the look in the line of sight. So I'll leave you to sort of have a go at that for a few minutes, and then we'll move on to a different type of faulting. If anyone has any questions, please just raise your hand. I'll try and get to you, John. But yeah, yeah, the two Johns will get to you. Hello.
So are we just playing with the parameters and trying to get the right slip fault to look like one of the examples a bit further down?
So at the moment, just try and understand what each parameter has as an impact on the displacement that you're seeing.
Okay.
So don't try and have a look at the real world example until we've gone onto the line of sight, because basically what I want you to try and do is come away from this with a feel of what each parameter has an impact on the uplift or the substance or the surface displacement you see. Yeah. So try and a good thing to do is try and break it as well. Go up to a slip of 100, see what that has. Go down to depth so you can't see it anymore, but just sort of parameter test this and see what you can see.
Yeah, I say. The actual length.
Okay, hopefully you all had a chance to break that and see what it looks like. So that's the strike slip example. So the question that came out earlier was, can we differentiate between different types of faulting from the surface displacement we see? And the answer is sort of yes, very, very much so. So if we go to and we run the next code block, you can see we have the fault parameters. We have a dip of 45, rake of 90, and a strike of 90. So we've got a thrust fault here. So it's kind of what in our components of surface displacement does a thrust fault look like. So in east-west, we have a sort of, as the fault is thrusting, it's moving material out of the way, out of the sides. So you can see you have material moving this way, moving westward, and material moving eastward as it's thrusting up. In north displacement, this one's quite confusing. It's quite a complicated pattern, but essentially what you need to think about is that the southward motion is associated with your footwall, and the northward motion is associated with your hanging wall. So as the hanging wall is being forced on top of the footwall, you see you have northward motion here at the tip, and then a northward motion as you're pulling material up. But the two are sort of cancelling out against one another because you only have the cumulative displacement of the fields. So that's why you're getting this sort of complicated pattern north-south. The vertical displacement, a lot more simple. You just have a thrusting fault, therefore you have sort of everything going upwards, but you can't really see it. There will be a secondary lobe of subsidence on the other side where your hanging wall is moved slightly downwards. Again, you can see all of this in the 3D vector field. But from this, so these are your sort of end members. You can turn this into a normal fault if you want to, by putting a minus sign on your rake or just inverting your slip. And that can show you can get sort of the opposite out. So it's easy to see how that would differ. And then what we do is we have our components of north, east, and up displacement, and we're going to project that into our line of sight. So we have an incidence angle of 38. So this is, I was kind of hoping I'd have a pen here. You use this. There we go. So say I'm the satellite, our incidence angle is that. Our heading is, if we have, so the Earth is up and the satellite's doing a polar orbit, we have a heading going this way. So for ascending, that's -10, and for descending is -170. But because of that, we get different amounts of each of the north, east, south components in our line of sight. So north, south is roughly sort of 20%, east, west, 70%, up, down, we're getting about 80, 90%. And that's just because of the orientation of our acquisition geometry. But what you can see from here is whatever you put in the one above, so whatever this fault is, below, we're going to convert that into line of sight. So at the moment, we've got the ascending, and we've got that ambiguity of, we don't know whether something's moving sort of westward or whether it's going up. So we only know that there's been movement towards the satellite, and that's why we're getting the sort of the lobes being forced like in a westward direction. So what I want you to do now is, there are a few parameters now you can play around with. There is the parameters of the fault itself, and there is the incidence and azimuth. So what you should, so the azimuth, sorry, is the heading. So if you imagine, so if we shift that azimuth to north, we'll get all the displacement from the east-west, but none of the north-south. If we were to shift that to 90 degrees and say we had like a equatorial orbit, we get none of the east-west, just north-south. So you can start to see how the geometry of the acquisition affects what you actually see in the InSAR. So you can have a play around with that and have a play around with the faults themselves and see what each of the different faults will look like in the line of sight. Bearing in mind that there are two real acquisitions that we're going to be using, that's -10 and -170. So if you want to see what your fault will look like in a real acquisition, use those as your parameters. Hello.
When you had a real acquisition, we also have a range of incidence angles.
Yes.
Are we going to be dealing with that like somewhere in the notebook, or
So,
what do you do?
So at the moment, we're just using an average across the frame. So the idea here is that we don't have actually that much of a it's not that big of a frame, so hopefully the angle change shouldn't be too much. But if you're going to do this properly, like John said, on the portal there are the unit vectors, and those unit vectors tell you how much of each of the displacement fields you should be getting. And that would be the proper way to do that. But it's in our toy model, we're not going to bother with that. So yeah, have a play with those. Again, see what the extremes look like. See what, if you have an earthquake that you're particularly interested in, see what your own example might look like. One thing that is quite interesting is if you have an example that has sort of, you're getting the depths from seismology, those depths you'll see produce quite a small surface deformation. So the InSAR usually tends to put the depth more shallow than the seismological solution.
Oh, well, I was assumption. Just, I mean, it's just, I was like, oh, it's really weird. It makes sense. But, yeah, it's when you add it, using within the construction.
Okay, I'm aware I'm moving on quite quickly, but I want to get through this so that you can go back through and play with it at your own time. So next we'll be moving on to some real world data. So this is an interferogram taken from the Leeds earthquake portal. So this is an earthquake in Greece. It's magnitude 6.3. It's got a lovely signal, lovely interferogram. Not going to tell you too much about the mechanism. Well, actually, I'm not going to tell you anything about the mechanism. You guys can figure it out yourself from what you've been playing around with. So what we want to do is at the bottom, we have some code that will generate you a forward model based on the same way that it was doing before, in line of sight. The forward model that you generate is in the middle, and the residual is at the bottom. So what you want to try and do, what we're trying to do is get our model as close to the real world data as possible, and our residual should just look like atmospheric noise if we've got a good model. So you can tell from this, the starting model is not fantastic. I'll give you a clue. This is not a strike slip earthquake, and it is put in as a strike slip. So I would initially have a think about whether this is a thrust or a normal fault, and then from that try and refine the rest of your parameters to try and see if you can get this residual to have basically no fringes in. And I'm going to do the same thing, but don't copy my answers.
Just raise your hand if you need any help. Yeah, so the GitHub is a live link, has a possible binding to finance for. We will need to ask Andrew to update the number of that teaching for better declaration. You may. When you did the global send change, do you know how many it did? Just the one card. The number.
Yeah, it's what should be very long. Actually, all the time, so that was the point. And I actually see it in possibly just for the first usually.
Okay. Did it need to be pushed?
Whoops.
I
Yeah.
So it's one important bit of information from this is that this is an ascending frame, and by the Leeds convention, motion away from the satellite is positive. So that should give you some indication of what the mechanism should be. What's everyone's RMSs looking like? Anyone got one that they're happy to share? Oh, there are questions in here. Ah. I didn't use the chat. How do I? Ah. Do we possibly quickly explain how to interpret the first example again? Which one's the first? That is the first bit. Okay, so that's this bit. Yeah. Okay. Yeah, the question online was how to interpret the first example. So what we're looking at here is the east, north, and vertical components of displacement that are caused by a uniform slip Ocado model. So the east, this is a left lateral strike slip. So the top half is moving sort of leftward or westward, and the bottom half is moving eastward. So as you like, it makes sense that everything at the top is moving to the west and everything on the bottom is moving towards the east. The north displacement, so as you sort of strike, as you slip, you're moving material from one side to the other. So for the top half, you're moving material south from this end and then back out northwards as you need to move the material somewhere. And the same again for the bottom, you're going northwards and then southwards. So you end up with a pattern that looks positive on both sides, and positive on the same side, negative on the same side, but they are actually moving different directions. And then the same with the vertical displacement is because you're pulling material from this side and adding it to this side, you end up with uplift on one corner, subsidence on the other, and the inverse on the other side. So it's easiest to see in the vector field. that's kind of showing you how all the components of displacement are moving. So this is the horizontal displacement, and then these are your vertical displacements. I hope that was a little bit more clear and answered your question. Okay, I'm going to move on to the next example. Well, actually, how close have we got? Is anyone happy to share? Anyone want to have a look? This is as close as I've got, so I mean that's not amazing, but it's got most of it. It's got the far field stuff. So what I'm looking for is, you see, like this singular lobe here is kind of matching this. I've got the shape at the back. I do have extra displacement here, so I think there's extra subsidence that I'm missing. But I think I need to start playing around with the rake to get that out, because I think it's slightly oblique. But yeah, I'm relatively happy with that.
See your parameters?
Yeah, sure.
My rate is 70. Like this should be like 0.
Yeah,
This should be.
it should be roughly. Yeah, I don't think you're ever going to get. So hopefully it should be basically all gone. But whether you need, so it's quite a complicated system. There is post-seismic. So yeah, there's a magnitude 6, a magnitude 5.2. Maybe you won't be able to capture it all. So maybe you need some sort of distributed slip. But for a first pass, doing it by eye, it's not bad. What do you reckon, John? Can you do better?
Yeah, a little bit, maybe.
Yeah. Okay, so we'll move on. So that was a what was that? It was a normal fault. So we're moving on to a strike slip example. So this one shows you just kind of how difficult this can be to do by eye and why you might need an inverse solution. So you might just need to try everything and see if the RMS reduces. But this is a really noisy signal. There is a characteristic four-lobe pattern of a strike slip event. Trying to fit that is going to be difficult, especially if you're doing it manually. But it shows you what some of these, when you're hitting the noise floor, they can start to look like. But there is still definitely a signal in there, as you can see from the unwrapped, and it matches what we would expect from a strike slip event. So if you guys wanted to try again, we'll do the same thing again for this one. See how close you can all get. Remember, keep your parameters and your RMSs, because at the end I'll show you the seismological solutions. I think they've been tweaked by John a bit to try and get a better solution. So there is an answer at the end. So keep your mechanisms. So if you want to take data from the COMET database, so it has all the information you need. So all of the input files for this are saved and you have access to them. They're just in binary format, but you do need some metadata alongside it. The COMET portal gives you it in TIFF format, but you'll need to just convert to a binary and then save the metadata. But it should be relatively self-explanatory if you look at the input data we've used for this practical to go from one to the other. Oh. Am I going till the app?
Really finish now. You do it. I mean, if you finish this one and then do the two, and then they can just start follow them themselves.
Yeah, okay.
Just so you've got a list of answers. You got a spreadsheet.
There's one that just prints at the end.
Oh.
Can't remember what this was. Was this 9? Oh, it's not. That's wrong.
Impression.
It's a difficult one. I definitely got this last time. Not that I wrote it down.
Right, is it? I think that sounds good. I'm back at 58.
One of the key metrics is if the residual is bigger than your original data, you're really going wrong. And if you do, that's a given if you're doing a forward model like this. But if you're inverse model, whenever you run a black box and you press go and say, give me an answer, always have a sanity check, because if your misfit is bigger than the original data, your whatever coding you've done, whatever modeling approach you've done, has gone completely wrong. Because a model should always reduce the misfit. It might not, you can't make it zero, but it should always make it less than the original data. If it's making it more, it's nowhere near the right answer. Also get a feel for how you're balancing your trial and error. So this is called a grid search approach with an inverse problem. So it's not a formal inverse, it's basically you try parameter varying it and try varying all the others. And at first you probably use the left-hand side, the unwrapped, because it's a bit easier to interpret. It's just whether it's green or yellow. So you try and get the magnitude roughly right. Once you've nailed that, you can actually start to use the contours, the fringes, because they show you the gradients. So rather than just the amplitudes, the gradients give you the shape. And that then is much more sensitive to your choice of parameters. But the shape's obviously affected by the noise of the atmosphere a lot more. It's a lot patchy.
Do this all day.
Yes.
Yeah. Very good. Yes.
Slow inverse problem.
Yeah, exactly. Yeah. Usually you just throw this to inverse and it gives you an answer. Okay. So again, there's a final example. So this one gives you some idea on what the problems might be when you're looking at larger earthquakes. Larger or deeper, they have much longer wavelength, so you might end up with part of your signal being off your frame. You've not caught it. Usually, what you do is stitch frames together if you can, but sometimes it's just not possible. So you will end up losing part of your signal. Also, when the fault gets to sort of this size, the uniform slip approximation that we've used starts to fall down a bit. So there may be multiple fault segments that have ruptured. There's a complex fault geometry that we're just not capturing. So trying to fit this in its entirety with just the uniform Ocado model is never really going to work, but it will give you a good first guess. So and it might tell you something about a portion of the faulting. So this one, I don't expect for you guys to get it perfectly, but you can match it quite well. And then once I'll give you time to play around with all three of them. I think you got about 8 minutes. And then when just before the end, I'll show you the final results. Again, the final results are from seismology with a little bit of tweaking, so they may not be actually what the focal mechanism is, because there is quite a bit of incongruity between seismic solutions and InSAR solutions. Part of what I do is trying to figure out what that is, but yeah, that's a different story. But yeah, so go ahead. Right.
So I'm just gonna-
We don't. Okay.
I'll be back and forth, but
Quarter past. Okay, we got a break after this.
We've got a break now.
Break now. Okay, right. Well, our meeting into your break, so you can have a go at this at your own time. They'll be available after. Again, I can't stress this enough. That COSeismic lib is an incredibly useful module. Use it. It's Python Arcada. It's very helpful. But I'll leave on the screen the 3 final solutions. So when you, yeah, I'll leave them there whilst we're at a break. But yeah, I'll hang around during the break if anyone has any questions. But yeah,
Maybe next two ones were only this. There are maybe.
yeah.
which is Greystone High. I'll type it. Yeah.
It's called, do you actually? Don't have That's fine. Yeah, I mean, I don't know, so.
Yeah.
Just check.
Yeah.
I think that's
Yeah.
Yeah. Dehua? Yeah, he's listening. I was just something. Yeah, I'll go and bring the people. So
We can chat.
yeah, it's recording all the time. Okay, no big deal. Fine, we'll bring the people. So 2 minutes more.
Okay.
That kind of just sort of news and yeah, there's have you looked at the limits?
Literally about everyone.
So all the people that gets in there.
I will.
You asked that in 3D question.
Funny guy.
No, sure, whether you know that one, I don't know.
What? That's
Yeah,
no.
I don't even-
No, it's not so expensive.
But yeah, you can pull that and then-
Right, welcome back. I hope that was a refreshing break. Thanks for returning. Thanks to everyone online for just waiting a couple of extra minutes. Hopefully you can see everything better this time. Please message if you're not seeing or hearing what you expect to. This second half of the session is to move on to another part of the earthquake cycle. Prior to this, we were doing the co-seismic earthquake events, the big sudden shocks, the big seismic shaking. This is more looking at the interseismic build-up of that strain between earthquakes and what it can tell us about fault slip rates and the deformation of the continent. So I've showed you the earthquakes. I mentioned a bit about the post-seismic. InSAR is used though for all manner of applications. Tomorrow you'll have the volcanoes. You've already had things about tropospheric water vapor. We haven't really covered landslides, glacier and iceberg and land substance so much, but those are two very important aspects of it. We do have another COMET InSAR portal looking at land substance in Iran, so I recommend also having a look at that as well. And then the GACOS, the atmospheric correction, was dealing with the tropospheric water vapor as well. So there are portals that serve all these sort of data sets. But for now, we're looking at the long term or the decadal timescales of interseismic. And we want to do that to gain understanding of earthquakes. We want to understand the driving processes that lead to earthquakes, the faults that are building up this strain that are going to host these earthquakes, and ultimately, can we usefully do this for society to inform seismic hazard? So we need to do more aspects of earthquake cycle to do that, to not just the earthquake. How it accumulates, how that is distributed, and how ultimately the constants deform from a science question. And seismology is really good at the earthquakes, and InSAR can only provide insights for certain shallow continental earthquakes. But where the geodetic techniques of GPS and InSAR do help is with these longer term or decadal term small displacements. Earthquakes quite large displacement if they're large earthquakes. What we're measuring here, because it's over many hundreds of years, is a fraction of what you get in the co-seismic. So if you get a meter in an earthquake, but it takes 100 years to get that meter, you're only going to expect a centimeter per year from the interseismic buildup. It scales like that. But we need to measure this at a large regional scale to do it. So earthquakes happen over a broad area I showed you on the continent, and to get that up across strain accumulation. So returning back to our picture of Turkey and the North Anatolian fault that runs through the north of Turkey, and our simple idea of how the earth works, the fault trace, the crust, the relative motion of the plates. We're now looking at this green interseismic accumulation of strain, where importantly, the fault at the surface is not moving. It's the deep shear zone at depth So again, you're looking for deep motion, but imaging a surface. So it's filtered through this upper 10, 15, 20 kilometers of the Earth crust. So it's always a filtered thing. We're not seeing anything sharp. Any sharp in the interferograms is to do with either earthquakes or creep along faults, or other things like landslides or subsidence in basins or something else. But interseismic is a very long wavelength and 100-kilometer wavelength process that we're looking at. So we've gone through that aspect of it now. So to illustrate that in map view, imagine your fault here. I've dotted it because it doesn't move in the interseismic, and this is the length scale. Build a fence from A to A prime, and this crust has been forced on its edges by something. So we will call that plate tectonics. Over time, depending how fast things are going, that could be 5 meters. And that gives you a kink in your fence that you've built across a very, very, very long field the size of a country. So that's your strain accumulation. Here it's not bent, here it's not bent, it's just moved an offset, but here it's bent. That's strain. It's a change in displacement over a distance. And you can imagine that accumulating, and you've built it up. And once you've built up enough, say that over 100 years, the blocks, the plates have moved 5 meters in the far field relative to each other. It's always a relative measurement. You build your new fence. What happens in the earthquake? So this is the interseismic period. You've bent a long old fence. You build a new one. You get that return. So that's what I showed you, that elastic response for that Turkey earthquake. And the elastic accumulated snaps back. So it's no longer bent. It records the long-term offset. So this is a fence. So it'd be true of fence. You see, it'd be same with river stream profiles. That after the earthquake, you'll get an offset, and then the river will have to readjust, and it tends to trickle down the fault, because that tends to be low, and then join back up. So, geologists and geomorphologists will get that long term. But we measure that in the earthquake, and we measure that in the interseismic. Those are the two things because they relate directly to each other. But that's the earthquake cycle and map view. That takes hundreds of years. That takes tens of seconds. That's why it's more dangerous. 10 seconds of sudden movement is a lot of shaking, a lot of hazard. So here's an example of that Darfield earthquake I showed you. The fence was built relatively recently, so it's bent an offset. It's actually offset in the earthquake over a very short distance. That's the co-seismic offset. It's not the interseismic. It wasn't built long enough to record it. That's a co-seismic step. It's over only a few meters. It shows you the fault really ruptures to the surface and it offsets it by a couple of cow hides. To measure the long fault, we can't do that with a fence. Nobody builds a fence, the long-term strain accumulation that's 100 kilometers long. That's why you need satellite-based or a lot of GPS in a line for 100 kilometers, which people do as well, particularly early on. But that's the fault through there. You can just see the rupture, the relative motion. Again, this is an example from the Turkey earthquake. You can see that offset that's recorded. Very near field offset. And of course, the greatest hazard is in the near field for shaking and pancaking in buildings, or if a structure happens to lie right on the fault, it won't have any chance because it will actually be offset. This is not offset, it's just heavily shaken. This is offset. But either way, because of the near field effect, you can see quite a catastrophic difference. Now, of course, some things have stayed standing. The ground floor would not, that would have disappeared. But it shows you that local site effects or local building effects can really make a difference. But otherwise, that's the kind of effect of the near field rupture. So, keeping with Turkey, this is the North Anatolian fault again. I'll show you some of that long-term InSAR, the time series average velocities we look at. But it's done at millimeters to centimeters per year. So it's hard to measure 1 millimeter per year. It's a bit easier to measure 10 centimeters per year. But there aren't many faults that go 10 centimeters per year. North Anatolian fault goes faster than that. The San Andreas goes, but not many faults go that fast on the continent. But that's what we're trying to aim. We're trying to push down that limit to measure. And what you're looking for is a change in color across it. Here, it means it's going west. Here, it means it's going east. Try and make it quantitative. These are kind of numbers. Going from here to here, it's about from 15 to just about 20. So that gives you a rough idea of how fast it's going from plus 15 to minus 20 or so. So it's going quite fast. So you can map it onto what the slip rate should be, that change in the velocities. And we want that for the earthquake cycle. How does that play out along here? Here, it actually, the earthquakes tend to unzip along the fault. Is that just coincidence, or is there some progression of rupture? But how does the long-term interseismic relate to where the earthquakes have happened? The large-scale deformation, how does Anatolia move westwards out into the Aegean? Can we get at the spatial variation of frictional properties on the fault? To have interseismic and this gradient from red, pink, white, light blue to dark blue, there's white along here, so it goes through the near zero. Well, that must be locked. It's not slipping at the surface. But there are bits along the fault that are creeping. So that tells you something about the fault frictional properties. So that is able to host a seismic creep over the years. They're not building up stresses in the shallow net. And we want to look at differences in rheology. How is Anatolia different from the Turkish-Iranian plateau over here, Saudi Arabia, the difference between the Black Sea, rigid versus not rigid, deforming interior. So we can get at that a bit as well. And as I said, the seismic hazard is always there. So pertaining to that, then this is the strain rate field. It's a measure, as I said, of how much the cross is deforming. This is from GNSS. And what we're trying to see is how does that strain rate map on to where the earthquakes are happening. As you can see, there's quite a good correspondence. Where you're building up pressure or stress by straining the cross, you then have to eventually release that. It's not quite one-to-one mapping, but it's pretty good sort of relationship. And we had a similar look in Eastern Turkey, where we can see the strain rate with GPS and InSAR, where all the energy is released. So that's the sum of all the seismic measurement, and how many earthquakes sort of in a Gutenberg, Richter, how active an area is, the A value, where those are occurring. And again, you can see it maps fairly well. Where you're building up strain is where you're going to release it. And areas that don't build up strain don't seem to have earthquakes, but sometimes they do. So it's not a cast iron. There's still an understanding of what these local effects might be, but it's a fairly good relationship. And the seismic hazard and risk side, we're strongly motivated to do that through some of our programs, because over 50 capitals shown here, the least economically developed nations lie in areas that are straining. So strain rate here is therefore a proxy of seismic hazard. How big those cities are in terms of 1 million people or 10 million people is a measure of their exposure. And then their relative wealth is indicative perhaps of their vulnerability at a coarse degree. So if you don't have a rich nation, you might not be able to build resilient infrastructure to cope with ground shift. So these are those sort of 50 countries that if you're going to target urban disaster would be the ones you would go for. Areas that are straining very fast are going to have earthquakes, and a lot of people live there. So the ones we've looked at in the past, it's a bit at Santiago, Almaty quite a bit, and there's just all these large capital cities, but of course non-capital cities in those countries are also exposed. But that's the potential for ground shaking. And what tends to be happening is these cities are all growing, so they'll move that way. This probably won't be changing, because remember it's long-term build up, so it's not that this changes. And then the hope is to be able to increase this so that you can increase the resilience to these hazards. You're not going to stop earthquakes. We can learn more about earthquakes, you can't stop them, but we have to reduce vulnerability through building better buildings, preparing society for these events. And again, I showed you this before. This feeds into the Sustainable Development Goal 11 for sustainable cities and communities. We looked at some of the initial earthquake response. So what you can do in an earthquake. InSAR can't do much. That coherence mapping could do something in the initial response. Looking at aftershocks post-seismic feeds into here. Now we're more at this end. The continental strain rates, how fast the fault's going, how, where are they building up strain, how big could they be, how fast, and where are they? So this is an example from the early work that was done the first time this was done. So it's only really a 20-year-old technique to apply this. Earthquakes have been about 30 years with this technique because they're bigger signals, they're easier. This was going for smaller signals. So here, trying to measure, in this case, a couple of radians across the North Anatolian fault. So a few tens of millimeters per year. And similarly, this example from the East Californian shear zone as well. But what I want you to take home for these is we're looking for diagnostic shapes. There's this particular shape that goes across this concentration of that fence, that bendiness of the fence that's built across it that you're looking for in these. That's your strain concentration. So why is it there though? So we've gone over this a little bit. So just to reiterate in a different diagram, this bit is your fault. We're not quite sure what goes on deep down. It's a bit hard to image. You have to look at geological shear zones for that. But there's some aseismic creep in the lower cross. When you get hot enough, this can't sustain a brittle stress on it from the friction. It's going to strain. It's going to have a shear zone in here. Aseismic creep of some form happens at these hotter depths down there. So if you imagine putting out your GPS or your InSAR data there, you're recording the earthquake. This is the kind of displacements you get. On this side is your reference side. It's always relative motions really with this. On that side, you've got your long-term velocity. Here, it's your half your velocity because you're halfway across, and you get these steps every time an earthquake to recover that motion. And then you also have these post-seismic effects in the further field out here. So we've covered some of those. So co-seismic, we learn about the seismogenic depth. The interseismic and post-seismic, we're learning about the deeper crustal properties. Less about the crust or the upper crust because it's not moving. It's the bits that are moving. You can't really learn much about something that doesn't move. And we learn about those by looking at the spatial coverage, and we learn about the rheology, how the rocks are deforming by how they vary through time. So that's the post-seismic element. So that locked portion, your locked elastic lid, that bendiness of the fence is actually been modeled for a long time with just a simple arctan function with 2 parameters. So you can always make models complicated, but you've got to justify it. But you can learn most of it just by 2 parameters. Slip and how deep is this locked portion. So it's really sliding at depth, but it's locked in. So there's that locked depth, which I said is about 10, 15 kilometers. How fast is the fault going at depth? Might be 10 millimeters, 20 minutes, something like that. So those are the 2 parameters in the practical you're going to be trying to solve for. Earthquakes, you have the 9. Here it's even simpler. It's just a couple of parameters that we're after. You can change it. One of them is the rheology. You can say this side is more rigid than that side, which would then focus the strain differently. There'd be an asymmetry in the bendiness of the fault. It's very rigid on one side, it might stay a bit straighter, a bit bendier on the other. You can imagine things like that. You can have an offset in your fault. So these things are assumed to have the shear zone immediately beneath the locked fault. But if your fault was slightly dipped, your shear zone might be off to one side, so you get an offset. So there are other parameters you can play with, and they're usually further down the Jupyter notebooks. But this is called the screw dislocation model. So it's a simple approach to how we do it. And a screw dislocation, if you do an analogy with crystals, there's 2 sort of dislocations you get. And it depends on the insertion of an extra plane of lattices, whether that's perpendicular to this Berger's vector here. So it's basically these lattices. And that would be, if you imagine dikes in volcanic system, you're injecting something, jacking it over, and your extra thing goes in there. That's your extra plane there. That's more like dikes. For faults, the screw dislocation is where that dislocation line is then parallel with the Berger's vector, all these planes dislocation, and you're inserting an extra plane of crystals along that. So we are dealing with the screw dislocation approach here. And as I said, it's very simple and always starts simple. And it was when we did this compilation of how this was applied to faults, looking for this bendy fence, it was actually applied across the world in almost 200 examples where it did well enough in 100 papers. And they were going for the slip rates, how fast are the faults moving, because that's your first concern. And then the locking depth is a secondary concern, but basically the wider the locking depth, the deeper it goes, the bigger the earthquakes, because that fault width, W, can be larger. Doesn't necessarily have to be, you can break only part of the seismogenic crust, but a 10-kilometer wide fault can have only a 10-kilometer deep earthquake or wide earthquake. If it's 20, you can double it. And you might expect some scaling, that means you get more slip as well. So it's another important one to know, but the slip is the primary use. And when we looked at this analysis, we were trying to say, well, how thick was this? So earthquakes tend to be about 12 kilometers, but they have a range about how deep they go. The interseismic tends to be about 16. But as you can see, there's quite a spread on these variables. This was done for different parts of the world. Iran, we break it down to Tibet. And you're trying to map, where are the earthquakes happening versus how thick the crust is, how elastic is the crust, and how hot is how much heat flow goes to it, how thick is the lithosphere. Trying to match and correlate these things. There's not much correlations to bear out. Basically, the seismogenic is usually less than the crust. So it's only the upper crust that's seismogenic. And the interseismic seems to be about the same interval as the co-seismic. So where you're building up strain in the locks portion is where you're going to release it. That's what we basically show. It's very intuitive, very simple. So this was done across quite a few areas of the globe, and on average we find it's 14, 15, but there is a bit of spread, but it happens, all the action happens over this depth range. So strain is concentrated largely around the faults. Now, of course, this being sort of our science of geophysics geology, is that indicative of the way all faults work, or is it just because you go to where the strain is concentrated because that's where you can measure it? We obviously, where we can't measure it, we don't report it. So there's a bit of a sampling bias there, which is it's very common in what we do. You go to where you can measure it. So increasing the work we do is to move away from the major faults that have shown to have strain concentrations to ask the question on the other faults, is that still true? By throwing a lot more data at it, improving the signal to noise ratio to see if it comes out. So yes, we can find faults now that aren't slipping at 10 millimeters per year, but perhaps 2 millimeters per year. Or is it become more distributed? Is it some other mechanism? It's not a shear zone beneath. Is it distributed, squishy continental crust of blocks? Still very much an open question that's debated. And the problem we're always going to have is when we start to move away from looking at the big faults to the smaller, is this filter. It's an elastic lid filter, 15 kilometers wide. So all of this deformation in this zone, you can't tell where it is. And you can tell if it happens at the surface, but the deeper it goes, the less well you can resolve it. It's a depth resolution problem. So if your blocks start to have shear zones that are closely spaced together, you can't resolve that just from surface data. There will be an indistinguishable overlap between the two. Another thing we can try and do is check our results as well. And again, you tend to look for things you can measure, so big rates 10 and 20, but compare what we measured today with the past. Does it have to be the same? We think it would be a priori, but it doesn't necessarily have to be true that the rates that it's accumulating strain today has anything to do with the long-term geological rate. And there were some notable exceptions where geologically the offset of streams and displacement of terrace rises that were dated over tens of thousands of years looked to be going a lot faster than what we're recording today. So it was suggesting that what you measured today was not suitable for trying to long-term extrapolate. But as more and more sort of data came in and reanalysis of some of it, it does look to be a fairly close relationship. What does matter there is where in the earthquake cycle you're measuring. If you measure the interseismic rate just after the earthquake, the problem is you get some of the post-seismic. And depending on the relaxation of the mantle, that can really contaminate your results. If you're late into the earthquake cycle, you're probably measuring more representative interseismic. But it's still a sort of matter of debate how representative of what we measure today to the long term. But the key points I want to take from this is where we've looked, interseismic strain is localized around the faults, so that's definitely true for the big ones. We can use a 2-parameter model to understand most of what we need to do. You can do more, make it much more complicated, look at variations along strike, adding creep, you'll add in creep in the practical. So where it's not locked in the upper surface, you can make it a bit complicated. That rigidity contrast, the offset, things like that you can do. InSAR and GNSS are good at this, particularly for faults that are like east-west strike-slip faults that are moving east-west. They're not so good for dip-slip faults, not for slow faults, not for motion or south. Yeah, so you can't do everything. It's not a panacea. And on average, the geodetic fault slip rates do agree within the normal sort of geophysics geology uncertainty bars that are quite large with the geology rates. And the post-seismic deformation really does occur commonly after earthquakes and can be quite a large fraction of the earthquake. So you do have to think about that when you're measuring your interseismic. So we ignored the finite width of that shear zone. We said it was a dislocation, a bit like in a crystal lattice, a slice through. It's actually likely to be a wide ductile shear zone that's accommodating the strain. Those elastic properties, we don't do complicated 3D-dimensional models. You can do that have more rigid areas and more squishy areas. Post-seismic really needs to look at both the afterslip on the down dip extension and fault and the viscoelastic relaxation of the ductile lower mantle. So there are a lot more complicated post-seismic modeling you can do to look at the rheology of the continents, and people do look at the viscosity, whether it behaves differently. Spatial variation, slip rate, and locking depth along strike. We've not done that, but lots of people do. Dehua is leading the next practical session, does that as his PhD. And as I said, this creep with depth as well, which we see in places. So I'll run you through and just finish the second half, a specific example from the North Anatolian Fault and how that's built up from the COMET group here in the UK. So just to show you how the era of big data sort of punched through from the early observations 20 years ago of interseismic strain across this region to more expanded coverage that was done using MRSAT data. Looking at the sort of noise, comparing it to the GPS, it seems to match well. Still quite noisy at the plus or minus 5 millimeters per year, but getting a 20 millimeter per year gradient across, well, displacement across there. To even more data that breaks it now down into fault parallel and vertical velocities and starts to look at uncertainty, confidence intervals on the slip rates. So here, 30 millimeters to 20 millimeters per year, but with plus or minuses of about 5 millimeters per year. Looking at creep and where that creep occurs. So bendy fence, long-term seismic. Something that looks a bit more like an earthquake, but without the earthquake is a seismic creep. So you get a discontinuity of the circuit. So that's been the sort of change over time to look at these areas and moving really to not just single tracks of data that are 70 kilometers wide, but looking at now whole regional tectonics. So here we've got the average line of sights over the MRSAT period from multiple tracks. Each of these on the ascending and descending, so you've got both directions, coupled with lots of GPS data, improved on mapping, which you might have covered this morning, to improve it and reference it with the GPS gives you much more a regional velocity field now. So rather than just getting these bendy fences over the fault, we're looking at whole continental scale velocity fields. And you can break this down into horizontal and vertical, which is useful here because there's a lot of horizontal east-west motion as Anatolia moves westwards. And the vertical ones are much more related to probably local substance area. You don't expect much vertical motion. We've tried it in some places like New Zealand to look at the uplift of mountains, and you can sort of measure 10 millimeters per year in some areas with InSAR and compare that to long-term evolution rates, exhumation rates, but that's a bit harder to get in some areas because the rates are quite small and they're very long wavelength. But you can do it over big scales if you've got a good GPS reference system. So InSAR is great, but it's all relative, so you need to pin it with GPS the best that you can. And this is now the sort of latest scale. We've got all of it now, and you can see westwards motion here, negative east, 20 millimeters per year. You can see the whole block of Anatolia moving relative to a fixed Eurasia in the north. Marks out the North Anatolian Fault, creeping segments, and the East Anatolian Fault here that hosted the earthquakes from last year. So building up the pattern of strain across here, what would be better in future is be able to map that strain onto where the earthquakes are going to happen in future. And then this vertical deformation that we see here associated with water vapor. So water substance. And from that, you can get an estimate from the velocities by measuring the change in velocity with distance, the strain rate. How does that velocity gradient map in space? And then that sort of gives you a heat map of the maximum areas of shear. So along here, a given, this area was picked because it was fast enough to know that we should get it with GPS. It's known the North Anatolian Fault's accumulating strain, the max shear of hundreds of nano strain there. With the Sentinel one, the InSAR, it sort of cleans it up a bit where you don't have much GPS, these white triangles. It localizes the strain more, so you know it's on the fault. So it does add value where you don't have lots of GPS. Turkey, there's already lots. California, there's already lots. Japan, there's already lots. But in areas where you don't have many, the InSAR can really help you with trying to measure these velocity strain wave fields. So if you look on the COMET InSAR portal, all that data is available to download. It's even more complete now. You can use the systems that you've been shown to get out all the interferometric data. That's quite a pain to process, thousands of interferograms. There's now 2 million interferograms on the portal. Using some of the time series analysis, the LixBAS software, you can then get the time series data, which then gives you an average velocity. Those velocities are what have been shown as maps. From those velocities, you can get strain. And you'll go through the practical at the bottom. If you have in your own time the desire and curiosity, you can go and look at the strain wave as well. So I'll just lead you through one particular example of this slip rate and locking depth for the North Anatolian, going from west to east, and what we learn from that. So we're solving for this slip and dip again. There's an extra complexity when you look at large areas, is the rotation of Anatolia. You have to account for the fact that this whole area is moving, rotating blockwise, that you have to account for, so you don't overestimate the slip. Once you've accounted for that, you can get at the slip rate. And I said about the creep. Sometimes you have to account for the creeping segment, so you're allowed to introduce more parameters for that as well. For creep, you need to know how much it's creeping and how deep it's creeping. So just to say what that creep is and is not, the interseismic shear zone at depth below 15 kilometers, this dislocation creep down here, that's your slip rate. When we say fault slip rate, we mean sort of that. This bit's the lock bit, not doing anything. It's accumulating strain, stressing the fault, and that is being relieved by some fault creep because the fault properties are a bit different here. There may be able to accommodate that by slipping freely without generating earthquakes. So we need to account for that in the model. So you have your slip rate and your locking depth, so D1 and S, and then your creep rate and your creep depth, C and D2. So it's just some extra parameters. And this can be done all across, and you repeat it in profiles all along through your regional strain rate field, looking for this to get those parameters out. So you can produce a map then of slip and depth. So for the interseismic practical that you'll do next with Dehua, you've got this as a simple model. It's an east-west striking fault. Here's your fault trace. This is the displacement across it, fault parallel velocity. That means motion's going that way, it's going that way. And imagine you've drawn a profile across it, your fence, you're looking at the change in that. This is your profile from south to north, how much that fault parallel velocity is changing. And this is for a fast, something going 20 millimeters per year. So it's got to go from 10 to -10. That means the fault's slipping 20 millimeters per year. And it does it over a wavelength of a few tens of kilometers. That's its locking up. A slow model, half as much, gives you half the displacement. So that's the slip you're after. So you're looking to match amplitude side to side. To get this parameter, it's a lot harder because it's a lot subtler. So now there's not much difference between them. For the same slip, they eventually asymptotically have to be the same, the far field plate rate. But if you double the locking depth, which is quite a lot, you can see there's not a ton of difference between them. So your sensitivity is in this sort of depth distance range here. You're looking for a long wavelength blue, if it's deep, short wavelength red, if it's shallow, that locking portion. It's the filter, that filter wavelength. So I will now lead you through the actual practical, but those are the sort of parameters you want to play with and build up in the complexity, go through it, start simple, and then work through the individual exercises. But before we do that, should we just pause for some questions from the floor and also online? Milan, if you're okay to help. Yes, at the back.
This is a 2D profile. To do 3D, you just do a whole bunch of columns along the rim.
That example did that. You can actually do it more, do it a bit more complicated than that, and do it like a slip, an earthquake slip patch, but do them deep. So Dehua done that before. And that gives you a bit more complexity to it. And other research groups typically do that. But you can easily do it with the profile. Any other questions from here? And then just a couple online. What are the challenges in separating interseismic strain signals from post-seismic and co-seismic deformation in InSAR time series? And how can advanced processing techniques address these challenges? Thanks, that's a good question. So it is a challenge. So as I said, the earthquake is contaminated by post-seismic. So you want to pick the shortest interval of interferograms crossing an earthquake as you can, but you'll always have some post-seismic in there. If you're looking at the time series, you'll have to account for the co-seismic offsets. That's what we have to do at the moment, is figure out ways to do it. Now, you can either break your time series into two, so you have two long-term averages, but you lose some of the advantage of having a long time series. Two time series half the long added together is not the same as one long time series in terms of noise cancellation. So another option is you solve for an offset in your time series. So rather than just trying to get your average velocity, you solve for two parameters. How fast is it going, a co-seismic offset, and assume it's going the same velocity afterwards, or two different velocities. And that we've tried different things, but you can build up the complexity like that to an empirical solution, or use something like the GBIS software and take out the co-seismic earthquake, try and solve for the post-seismic, and then get your interseismic. There are different ways of doing it. I'd say probably trying to estimate what happened in the earthquake and removing it is the best, but it's a bit more effort. An empirical offset function is easier to apply systematically, so that's what we've chosen for other approaches. And then there'll be even more advanced things you could probably do as well. The screw dislocation is only for strike slip faults. Yeah, so we have been, because it's easy, we've largely done strike slip faults, and because the signals are localized around there, it is more complicated to do it on dip slip faults. There are solutions for it, dislocation solutions. It does matter to include sort of gravity in the problem a bit more. We don't tend to get as much strain localization around it. We haven't investigated it quite as much, but yes, you can do it for it. It's just not in any of our sort of routines to do it. How can I fix an InSAR time series velocity map, for example, in a Eurasia fix? So yes, the way we do this is to use the GNSS. You can either make it up if you've got a stable Eurasia and say they're all a zero boundary condition, so you impose a boundary, or you tie all your InSAR, which is the better way to do it, to the GPS. So you project the GPS into the line of sight of the InSAR and minimize the difference between what your InSAR says and what the GPS says it should be. That tends to be the way we do it. But otherwise you could just pin it to one end, but it's always relative. It does need sort of referencing if you're looking at long wavelength signals. Is there any reference to know about the meaning of strain rate tensor components like dilatation, second invariant? Yes, so if you look in the papers that have been published recently on these velocity fields, so Chi et al. 2022 on the Haiwan fault has some definitions in the supplementary material of the second invariant and dilatation. Watson et al. 2024 probably does for the Iran velocity field, again in the supplementary, to some of the equations for the strain rate tensor and its components to get the max shear. So yes, they do have those, and in a stress strain textbook as well. How long should a post-seismic signal last after the seismic event? Yeah, that's a good question. So it decays. So it has a characteristic decay time scale. You can imagine this is a logarithmic function with some time constant. So it keeps going, would be argued. It trends into the interseismic. It's unknown really, is it a universal amount of time? Is it some examples of Iran, that time scale was months, but it can be that you see viscoelastic response maybe 50 years after some of the biggest earthquakes if you've got the right kind of rheology. So yes, it can persist for a very long time. So you need to measure really long time series to get it. How should we eliminate the co-seismic post-seismic? So I went over that solving for the co-seismic and post-seismic, you solve for it empirically. So I did that one. What are the limitations of current InSAR-based models in capturing the full complexity of strain partitioning and fault networks, and how can these be overcome? The limitation is how closely spaced these fault networks are. As soon as they get to within a few tens of kilometers, you can't really resolve them as well. And because we're always measuring the surface, I'm very reluctant to say that you'd ever be able to truly resolve them, even if you beat down the noise a lot more. If they're really deep shear zones, closely spaced, you physically can't with this approach do that. I think you need to bring in other information, I think, to set your priors a bit better. But yes, I think there is a limit to what we can resolve. Okay, I think we've covered all those. Let's straight into the practical, if that's right. Oh, thank you. You've got just about an hour now. I think we'll wrap up a bit. Well, we'll see how it goes, and then we'll wrap up by 5. Is that correct? Yeah. Yeah. Thanks, Ryan.
Thank you, John.
Let me stick.
Okay.
So, is there more coffee?
It's built.
Yeah. Open this one.
Okay.
Yeah.
Yeah.
The PPT is in this. Yeah. The PPT is here.
Yeah, just a second. So first of all, I'll duplicate the display because it will be better for you to provide afterwards to the practice. For this, I will connected. So now we'll share the screen again. And what was that? And this is the
No. Just the directory. It looks not about. Within that one.
that's for you, but they need the
Okay.
link. They need the link. So okay.
Just say it was.
Yeah.
Only construction scores.
Oh yeah, that's here. So oh, Pedro sent it already to everyone. So you can just mention that there will be just copy that one for everyone. Just be sure that they have it. Now Jupyter notebook is set. You have it here. I'll run it, and there is your presentation, so you can do whatever you want.
Okay, thank you.
Okay. Yeah.
Okay. Hello everyone. My name is Dehua Wang. Welcome to this COMET practical on interseismic strain accumulation. So during this practical, we will show you how to use the InSAR velocities to study the interseismic deformation and modeling the interseismic deformation, just using some simple model. Okay, now before this practical, we need to import required modules. So we can just run this cell. Hope everyone can follow me. As it is already introduced by John, the earthquake cycle can be divided into 3 phases, which include interseismic phase, co-seismic phase, and post-seismic phase. So during the interseismic period, we think that the fault is locked towards the surface, but is accumulated strain at depths driven by external force, such as plane motion. And during this practical, we choose to use this simple dislocation model to modeling the interseismic deformation. And in this equation, this S is the slip rate below the locking depth, while this X is the perpendicular distance from the fault, and the D is locking depth. So you can see that the shallow part of the crust is locked, while it is freely slipping below the locking depth. Some people will ask, will ask that why, is there any other model that we can use to model the deformation? Yes, we have. We can see that, we can show this. We can see that start from this simple dislocation model. we can consider the horizontal shift of the deepening shearing part of the fault. You can see the fault location maybe have some horizontal shift. It may be not localized on the surface stress. You may be shift due to the deepening angle. So you can just add the AL in the equation. And you can also consider rigidity contrast between the two sides of the fault by adding a rigidity ratio in the equation. You can get more information about that from this paper. We can also consider block rotation at one side or two sides of the fault. For example, along the North Anatolia fault, the Anatolia block is rotated. So you can using a zeta in the equation to represent the fault parallel component due to block rotation. We can also consider viscoelasticity and the thicknesses of elastic layer using different model. But this cannot be presented using some simple equations. But you can do this using some finite element modeling. So you can do that. You can also model in 2D velocity field using fault patches. You can divide the fault plane into a lot of patches and then modeling the surface velocity fields you get. And you can also using some block models to modeling the velocities. You can also directly model the strain rates for slip rate. You can calculate strain rate and directly modeling strain rate using some codes. So you can see more details from this paper. Okay, so we know that there are a lot of codes that we can use to modeling the interseismic formation. So please read some paper about that. Now let's focus on, go back to this practical. Let's start with this simple model. We will choose this on North Anatolia fault to be the example because this fault is very active, is very long, it already caused a lot of earthquakes. So, and it is a structural fault. Let's start with some, let's start by generating some synthetic velocities using our screw dislocation model. So you can set the parameters manually, set the slip rate, locking depth manually, and show the interseismic deformation in 1D and 2D. So in the left side, in the left figure, you can see how the velocity look like on 1D. You can play with these parameters. You can adjust the slip rate and locking depth in the codes and to see how these parameters change the pattern of the 1D velocity profile. You will see that the slip rate will control the step size of the 1D profile, while the locking depth will control the gradients of the velocity profile. Normally, a large slip rate will cause a large step size, while a large locking depth will cause a gentle velocity gradient, a smaller velocity gradient. So in the right side, you can see the velocities in 2D, assuming that the fault strikes from west to east. But we know that we get what the velocity we get from satellite is in line of sight direction. So we need to understand how to use the line of sight direction velocity to study the interseismic deformation related to faults. So we can run this cell to see how the velocity, the fault parallel velocity looks like in line of sight direction. You can see that the top figure is the fault parallel velocities, while the bottom is the line of sight velocities from satellite. You can see it is a little bit different. If you use 3 profiles along the range direction, you can see the 1T profile of launch side velocities will be a little bit different from the for parallel velocities. You can see that the range is different. You can also see that the launch side velocities are different at near range, mid range, and far range due to the change of incidence angle. So based on this figure, we must know that there are 2 strategies to modeling the deformation. One strategy is that we can modeling the launch side velocities directly by projecting for the parallel velocities into launch side direction. And another strategy is that we can decompose the launch side velocities into for the parallel components, for the perpendicular components, and the vertical components, and modeling the for parallel velocities along. So doing this practical, we choose to use the second strategy. We will decompose the velocities and get the full parallel velocities and modeling that. So now let's plot the input launch side velocities using 2 LIXA frames, one ascending and one descending. Let's load the velocities. And now let's plot the velocities and also the fault trends. So we will get figures like this. So let's look at these 2 figures. You can see 2 different colors in these figures. You can see red and blue. So does anybody know that what these colors mean? Normally, the red means towards satellite, and blue means motion away from satellite. So if you already know the launch side direction of the satellite, you can use this to know or to understand the nature of the structuring fault. For example, you can see that in the ascending figure, the south side is red, the north side is blue. Well, for descending figure, the south side is blue, a little bit blue, relative blue, and the north side is red. So then we can know that this fault is definitely a right lateral structuring fault. So this is very important. You must make sure that the figures the velocity you get matches the things that you already know. If you already know that the fault is right lateral structuring fault, you should make sure that the velocity matches what you already know. If it doesn't match, it means something wrong or something new. Okay. Now let's do the decomposition. So we have 2 observations. We have ascending velocities, descending velocities. We have the directions. We have the incidence angle. We have the heading angle. We also know the strike of the fault. Using this kind of thing, we can do the decomposition. But from the equation, we know that the input are 2 observations, but we have 3 unknowns equation. So it means that this equation is unsolvable without any extra assumptions. So as the North Anatolia fault is we can say that it's a relatively pure structural fault. So we can assume that the fault perpendicular components are zeros. Then we can get this simplified equation to this one, and then we can solve the equation and we can get for the parallel component and the vertical component. Let's run this. But before that, we need to make sure that the grades are the same, because the ascending velocities and descending velocities may be on different grades. So you should regrade the velocities to make sure that you can perform the velocity decomposition for shared points. So you can just run this cell. It'll be slow. Now it is regulated. After that, there's another problem. You can see that if you get your velocities from Leeds path, then the two velocity fields are relative to their own reference pixels. So you should make sure that the two velocities should be under the same reference system. So to do this, you can choose, for real practice, we can choose the GPS velocities to be the reference velocities and reference the InSAR velocities to GPS velocities. That is for real practice. But for this, we can choose another simple strategy by choose a region or area in the velocities and use the mean of the velocities within the area as the reference. So we can reference the velocities to the same region. And then we can do the decomposition. Please run this cell. Now we can see for the parallel component and the vertical component from the left side velocities. So from these two figures, you can see that you can observe the different pattern at two sides of the velocities clearly from the four parallel components. So it means that, yeah, the South Anatolia or the North Anatolia fault is definitely a structural fault. But while in the vertical components, you can't see the different pattern two sides of the fault. So it means that the thrust motion along this fault is not very obvious. Okay. Now we can profile for parallel velocities. Before that, we should transform the longitude, latitude coordinates into UTM coordinates to help us better calculate the distance. So, because finally the model we use should have the distance in kilometers. So we need to do this transformation. And after that, we can use two coordinates in this region and extract the velocities and get your profile. One thing you should keep in your mind is that this profile should be perpendicular to the fault strike. This is very important. That's the assumption, the best assumption from the equation. So that you should remember. Then you can play with forward model by setting some parameters. You can set the slip rate, locking depth, and constant offset, and see what the forward model looks like and how the forward model will fit the observations. And you can also calculate the RMS misfit to evaluate how well the model fits the observations. And you can play with these parameters yourself and upload. I think this is another link. I think you can send your best model using this link. Okay, is anybody got this link? I think this is only a link from my side, I think. Yeah, just play with these parameters. Normally, what you do is you need to minimize this RMS misfit. So from this practice, from this profile, you can see that the step size is a little bit small. So you can let the slip rate to be a little bit larger, like 20 millimeter per year, and run this cell again. Yeah, you can see now the RMS reduced a lot from 3 to 2.2. You can play with this. Yeah. Yeah. Now let's look at fault creep. Fault creep has been observed on several active faults, and one of these is North Anatolia fault. So you may get some creeping. You may observe some creeping signals along North Anatolia fault. So you can model this. How identify if this is creep signal or not? If there's a creep on the fault, you can see there's a large offset in the velocities across the fault. So this step is very large. It cannot be. It is beyond noisy level. So you can assume that yes, there may be a creep signal in the velocity profile. Then you can model this profile by adding some additional components in the equation. So in this new equation, this S still be the slipping rate under locking depths, below locking depths. Well, this C is the creeping rate on the shallow crust, in the shallow crust. And you can see that the creep, we think that the creep happened between the surface to the depths of D2, and the locking depths is depths of D1, and the creeping rate is C. And this H is the Heaviside function. So Heaviside function is a step function. It means that when your input is negative values, it will output 0. If your input is positive value, it will output 1. So it's just a pure step function. Yeah. So now let's take a new profile across a creeping part of the North Anatolia fault. So in this profile, you can see that there's a big step in the profile. So this step is very large. It's about 7 millimeters per year. So this is definitely beyond the noisy level. So we should be using creeping model to model this profile. So now let's do some forward modeling by setting the parameters manually. And yeah, so this S1 is the slipping rate, S2 is the creeping rate, D1 is the locking depth, D2 is the creeping depth, while C is the constant offset. Well, SC is the location of the fault. So you can play with these parameters manually. So for example, you can see the creeping rate may be a little bit small in this case. So you can let it be a little bit large. Maybe this is 7. You can maybe 8, 9. Now how about 9? Yes. Yeah. Please play with this and make sure that you can minimize this RMS misfit. Yeah. You can also share your best model using this link. Yeah. Yeah. Is there any I send this link? Yeah. I can send this link. Sorry. You sent? Yeah. Okay, thank you. After you send that, you will see other responses. For example, if I just send my, for example, 23, 9, This one should be 18. And the 7 minus 8. And this to be 0, and also send my RMS misfit 2.198. Okay. 107. Okay. And then I submitted. Okay, we can also see other people's responses from this link. Okay. I think if this is forward modeling, it depends on your experiences, how you understand the model, how you understand creeping, how you understand the locking depths of the fault. So for now, this RMS misfit is 2.19. Is anybody can get lower RMS misfit? Lower than 2? Yeah. Yeah.
This topic is low block transfer dance always creeping. It is creeping because if you look at this profile, if I think most parts of the look, if it's like noise, along the fault, below the left side.
You mean?
If some noise along this fault, the left side. Yeah, if I remove this data, data, it looks like locked fault.
Yeah, so that's something we should test based on the observations. We can test without creeping component or with creeping component to see, see the misfit. That's the one way. Another way, there may be other tools can detect this. I think there's other tools can focus on creeping sections. Other geologic tools or geophysical tools can focus on creeping sections and to get if it is creeping or not. Also, there may be some other GPS stations can get better results. Yeah.
Another question is a lot of empty along the fault, fault, the north side. With a lot of empty value.
Yeah.
And if we some missing value, so if beside we mistake on the
yes. If there's some missing date in the profile, it will cause some problems. It will be very hard to decide if it is creeping or not. We should do more researches about that to get a conclusion. Yeah.
So why is empty?
Empty may be due to some coherence problem. Yeah, also due to the masking different, because we cannot say that the velocity is actually accurate. Some people process data, we are using different masking parameters to masking the velocities. So it depends on how we process the data.
I mean, pull apart basins, if you had a strike set with pull apart basins, that's where the vegetation subsequent agriculture was, and it would be a bit here. So it's just correlated with geomorphology. Unfortunately, likely to use data right where you need it. And fault source of spring because they tend to control the water flow. You're looking for a long strike consistency. So you look at one profile, but check the profile on either side, and creep extend for quite a few kilometers, then you'd be more confident.
So the type is kept the same along the whole fault, or is it different at the base location?
You'd expect the creep to exist for quite a few kilometers. That's what's seen in the computing zones. It's quite consistent long strike. Not the whole Amazonian fault, it's still a relatively short distance, but these are quite narrow profiles, so they're very susceptible to noise. But if you found it was consistent for a few kilometers, you think it was creep.
Okay, let's move on. Okay, there's some new responses. Okay, so lowest is 2.139. Okay, great. So this is the shortage of forward modeling. That's why we need to do inversion. Yeah, by sampling the parameter spaces automatically. Okay, now let's move on. We can estimate shell strain rate from 1D velocity profiles. So why we should study shell strain rate? Because shell strain rate can highlight the areas of concentrated deformation. Because if you look at the velocities, sometimes it's not very clear because of Berkeley rotation, because of noises. You don't exactly know where have the concentrated deformation. So we can just calculate the shell strain rate to highlight these areas. So we can get the state of strain in the lithosphere using this strain rate tensor. So you can see that these strain rate tensor are calculated from using gradients of velocities. Just a gradient of different velocities in different directions. For 1D, we can also use another method to calculate the shell strain rate by differentiating the dislocation equation, and we can get this equation. So we can calculate strain rate using these two different methods. One is from forward model. Another is from velocity gradient. So this is a little bit different because of the different way we calculate the shell strain rate. So you can get more information about this difference from the supporting information of this paper. You can see why the shell strain rate we get a little bit different. Normally, this is you can see that the magnitude of the forward model times 2 will be similar to the shell strain rate calculated from velocity gradient. But no matter what way we use, the shell strain rate, high shell strain rate focus on the fault. So that is very important. So this is from forward model, but if we calculate strain rate from profiles, you will see if we calculate shell strain rate from original beam velocities, the strain rate will be very noisy, and you can see the rate line. You cannot see where is the fault. So that's why we need to smooth this profile using some method. For example, mean filtering, median filtering. Yeah, and after we filtering the profiles, we only see very high strain rate localized on the fault, while other area, the shell strain rate are very low. Yeah. We can also estimate strain rate from 2D surface velocities. There are some methods can help you to do that. For example, you can read some method from this paper. You can get some methods to estimate strain rates. And remember, there are also other papers tell you how to calculate strain rate. Just read some papers. Okay. So in this practical, we choose to set the pixel size to be 20, and and firstly we downsample the velocities and filter velocities using median filtering method, and we get a filtered for parallel velocities. Then we get the east velocity component, component and the north component of the velocities, and then use these horizontal velocities to calculate the strain rate. Then you can get your maximum shell strain rate map like this. You can see that the high strain rate, the location of the high strain rate is very close to the surface fault trusses. So you can say that the strain mostly focus on the fault. You can also change this pixel size. For example, if the pixel size is not enough, for example, if it is 10, then you will get your fault parallel velocity like this, and then you get the east velocity and the north velocity, and then you calculate strain rate again. Now the maximum shell strain rate looks very noisy, and you cannot definitely know where is the fault. Yeah. Okay, now, just as we said before, we cannot set parameters manually to find the best fit parameters. We need to use some tools to help us to do this. So doing this practical, we choose using the Bayesian inversion combined with Monte Carlo Markov chain method, Markov chain Monte Carlo methods to help us find the best fitting parameters. So doing this inversion, we will try to minimize the weighted difference between the observed velocities and the model velocities. This W is the weight for every velocities. Normally, this is the covariance matrix of the data. By setting the sampling, by setting the parameter space for each parameter, and setting the total iteration number of iteration, then we can let the code to help us find the best fit parameters. This will take a little bit long, depends on, and the time you spend on this will depend on how large the iteration number you use. So in this practical, we're just using 10,000. But for some real practice, maybe we should use 100,000. Yeah, 1 million, maybe. Okay. Now, yeah. Let's plot the worker. So this worker will tell you how the logarithm explores the parameter space. A good inversion should let the algorithm to explore the full space. If it is logarithm only explore a little space of the parameters, it means that it will only give you a local minimum. It will not give you a global minimum. So you should make sure that your algorithm will explore the whole space you give, then to give you the global minimum. You can see that we set the space of sleep rate to be 0 to 40, to be 0 to 40, and the logarithm explore the sleep rate between 10 and 40. So it looks good for me, I think. And then we can look at the likelihood function value for each iteration. So this is the weighted residue for each iteration. You can see that this weighted residue goes down very quickly at the beginning and then stable after that. And this is reasonable because sometimes the logarithm will leave the local minimum and try to explore other space to make sure that all the space I touched, I can touch all the space and give you the best fit parameters. Yeah, and if it is go down and never come back, it means that your algorithm have some problem. It means that it only give you a local minimum, maybe. Yeah. Okay, we can also plot our best fit model on the top of profiled velocities. As we calculate the weighted residue for each iteration, so we can gauge the best fit parameters for this profile. So you can see that this is the best fit parameters for these velocities. So you can see the best fit sleep rate for this profile is 19 millimeter per year. Looking depth is 10.8 kilometers. Offset is -5. So the RMS is 2.1 millimeter per year. That is the lowest RMS you can get from the modeling. Yeah, this RMS is not very low because it depends on how noisy your profiles are. Now, we can also plot other things related to this modeling. So this will show you the histogram for each model parameters. For each, you can see that you can get the histogram for sleep rate, locking depth, offset. You can see the distribution of the models. Most likely, it's close to Gaussian distribution, but it's not a pure Gaussian distribution from these figures. So this is very important because it doesn't mean that the best fit parameters are the real one. So every inversion maybe have some uncertainties. So this figure, you can use this figure to evaluate the uncertainties of your parameters. For example, if it is pure Gaussian distribution, you can just using the standard deviation to be the uncertainty. Maybe 2 times standard deviation, 3 times the standard deviation, depends on you. If it is not a pure Gaussian distribution, you can use the 5th percentile and the 95th percentile to be the uncertainty of the model. Yeah. And then you can also compare, you can also show the correlation between model parameters by run this code. So this code will show you the correlation between the parameters. This is also very important. So from this figure, you can see, you can see that the offset, there's no strong correlation between offset and the sleep rate, offset and the locking depth. It means that the offset parameter may be a little bit maybe independent, yeah, in this inversion. Well, you can see a high correlation between locking depths and the sleep rate, and the shallow locking depths tend to have a small sleep rate. A large locking depths tend to have a larger sleep rate. So there's a trade-off relationship or correlation, strong correlation relationship in your modeling. So finally, you can also look more clearly about this correlation between locking depths and the sleep rate. You can see that also, although there is a high correlation between locking depths and the sleep rate, most of the accept models are focused on this region. It means that, yeah, there may be large correlation between the parameters, but I think most likely the sleep rate, the best fit sleep rate should be around this area. That's the figure can show to you. Okay, I think, yeah, in this conclusion part, there are a lot of links could be useful for you. And you can see there are some velocity decomposition codes can help you to solve large scale lifestyle velocities, decompose large scale lifestyle velocities. It's very useful. And you can also see there's some code can help you reference InSAR lifestyle velocity to 3D GNS velocities. Also, there's some alternative way to reference InSAR velocities to 3D GNS velocities using WellMap. And you can find the WellMap code in this link. If you're interested in other Bayesian inversion codes, you can just take a look at this link, GBS codes, which can model in the 2D velocity field. Okay, I think that's all from my side. Is there any questions?
When you drew the histograms with the distributions over the top, the fact that the slip rate and locking depth don't follow the Gaussian that well, is that related to the fact that what does that tell you anything about them? Is that related to the fact that they've got high correlation below?
Sometimes, based on my experience, if you set your space, for example, the real sleep rate is 10 millimeters per year, but your space is from 0 to 40. It means that, yeah, the reasonable parameter, the best fitting parameter for this sleep rate is 10, but your space is not symmetry. So this will cause the sampling to be asymmetry, and then cause a no Gaussian distribution in the results. That's the one possible reason. Yeah. Another reason maybe just because the noises in the velocities. Did any questions in mind? Yes. So okay. What? What the same thing? I'm sorry. I'm not. Let me see this question.
If you expand that at the bottom.
This one?
Yeah, you can do it.
Yeah.
So it took me some time to find it.
Yeah.
Exactly.
Okay. Thank you.
Yeah.
Are creeping and slow sleep the same thing? It's very hard to say. Creeping can be fast. It can be fast as the sleep rate. So we cannot say that creeping is sleep rate. We cannot say creeping is slow sleep. For some cases, the creeping rate can be the same, can be equal to the sleep rate under the locking depths. So in that case, we cannot say that this is slow sleep. So I think slow sleep just because of friction properties in some area. While creeping, a little bit different. It depends on the spatial and the temporal variation of the sleep. Yeah, I think but I think it's different thing, I think.